So we are going to start our first session of the day. And today's expert, Dr. R.K. Sharma, is with us. So let me tell you the brief about Dr. R.K. Sharma. He is working as a professor in Electronics and Communication Engineering at NIT Kurukshetra. He has received BSc Engineering degree in Electrical Engineering from Dayal Bhag Educational Institute, Agra. M.Tech degree in Electronics and Communication Engineering from REC Kurukshetra and PhD degree in Electronics from National Institute of Technology Kurukshetra in 1986, 92 and 2007 respectively. He joined NIT Kurukshetra in 1989. He has been a member of several research committees, board of studies and selection boards. Dr. R.K. Sharma has 100 plus research articles in international journals and conferences proceedings. His current interests include low power design of digital systems, configurable embedded systems, and human voice profiling. He is reviewer of reputed international journals. Dr. R.K. Sharma is a member of IEEE, Fellow of IETE, and Life Member of ISTE. So without wasting more time, I invite Dr. R.K. Sharma for his talk on low power VLSI design. Dr. R.K. Sharma.
Good morning to you all. In this lecture, we'll be talking about importance of low power design while designing digital circuits and systems. In day-to-day activities, you might have seen since morning till evening, you are doing various activities. You are attending the classes, you are going to the library, and then you are in a canteen, you are doing a lunch, and then after that again your body starts utilizing your energy for digestion of food. When you are thinking, your energy is being utilized for that activity, and there are many such activities where energy is required, and by the end of day you get exhausted, and then your body wants to have a rest, and then you sleep. Similarly, in the devices also, when processor is controlling various peripherals and various activities and processings are going on in processor, it is having those activities in a multiprocessing mode or parallel processing mode and all those things, and then switchings are going on. The activities are causing huge amount of switchings in the processor, as similar to the switchings in our brain. During the daytime we are thinking various things, so we are going from one thought to another thought, and these switchings are taking place, and these switchings lead to the consumption of energy. Whether it is a human brain or it is a central processing unit of a computer, all these switchings, they lead to the consumption of energy, and then finally the battery of that central processing unit gets exhausted. Because of large-scale integration and the ongoing trend of scaling, where we have gone from 250 nanometers to 180 nanometer, then 65 nanometer, and so on. Because of this scaling also, the leakage power is increasing tremendously. Switching activities are very huge because the processors, they are working in gigahertz range. So these performance activities, they have increased to a tremendous extent, and as well as because of this scaling trend, downscaling trend, the leakage power has also increased tremendously, and processors, they have stuck at a certain point where from where onwards performance cannot be increased, and entire focus has to be to curtail the power consumption, to reduce the power consumption. Power consumption is a major bottleneck in today's processors. You might have seen now we are not increasing the frequency of processors. Increase in frequency means increasing the performance, but Intel and all other processor manufacturing, the champions, they are not concerned about increasing the frequency. They are concerned about reducing the power, and that is why now trend is dual core processor, quad core processor. When two processors are working in parallel or four processors are working in parallel, the amount of activity or workload on a single processor is reduced, and therefore its power consumption gets reduced. Whenever any digital computation is done, it requires consumption of electricity. And huge amount of electricity is required if you consider all digital devices, laptops, PDAs, mobile phones, desktops, servers, and all those things. And if you consider this total number of devices in a country or total devices all over the world, so all these devices are working at a gigahertz rate, and huge amount of electricity is required. They consume huge amount of electricity. And second part is they have to be cooled. They have to be, their operating temperature have to be at normal value, and therefore cooling systems, they have to work continuously to keep these devices cool. They are working, they are consuming electricity. The air conditioners we are using, they also require electricity, and electricity is being generated from coal. Major fuel, major amount of electricity generation comes from coal burning. There are hydropower stations also, there are thermal power station also. And when coal is burnt, carbon dioxide is emitted. And this carbon dioxide forms a layer in the atmosphere, and what happens? The sun rays, which are short wavelength rays, they are able to penetrate the layer and they reach the surface. The surface objects, they get heated. But the radiations, which are long wavelength radiations, they are not able to escape into the atmosphere. They are trapped by the carbon dioxide layer, and this leads to rise in temperature. This leads to greenhouse effect. So ultimately what happens? Our computing devices, they are also responsible for greenhouse effect. Transportation is also responsible, but 1/3 of this problem is contributed by these power consuming devices. So that's why it is very essential to reduce the power consumption in devices. This will reduce the greenhouse effect. At the same time, it will increase the performance of devices. And if you have a mobile phone which consumes less power, then what is the advantage? Your battery life will be extended. If it is a high power consumption device, then it requires very frequent charging, or you require a heavy battery, and in that case your portable devices are no longer portable, and you will not like to buy such devices from the market. What is energy and what is work? You must be knowing the difference. What is energy and what is power? It's a +2 level fundamental. The speed at which energy flows is called power, and when energy flows, work is done. And depending upon the time available, you can supply large amount of power to do a work in that limited period, or if it is an extended period, you can reduce the amount of power, but in both the cases, amount of energy will remain the same. Because it is the, if you have a power along y-axis and if you have a time along x-axis, area of this curve is energy. If you reduce the y-axis component, then time has to be extended, but area will remain same. So when you don't have low power devices, what are the side effects? It leads to reduced amount of operation of a device because it gets heated and then it has to be switched off or it has to enter into a sleep mode. The weight of the device increases, its mobility reduces, its cooling cost increases. You have to use more costly cooling packaging have to be used for the device, and its reliability also reduces because ultimately rise in temperature leads to the junction failures of the ICs. It leads to electromigration inside the ICs, as is obvious from this diagram. There are many electronic failures inside the equipment or integrated circuit because of rise in temperature, and therefore reliability of this integrated circuit reduces. As we are scaling down the ICs, the size of ICs are reducing at a very fast rate. We have reached now 15 nanometer technology. This nanometer means it's a distance between source and drain of a MOSFET. It's a channel length of a transistor. And as this trend is going on, what is happening? The leakage power component is increasing. Before 70 nanometer technology, dynamic power was bigger than leakage power, but as we have reached 35 nanometers or we are going down than 35 nanometers, leakage power is dominating the dynamic power. What is dynamic power? When system is working, the transistors are switching. Your processor is working at a gigahertz rate. There are millions of parasitic capacitances inside the processor, and when it is working at a gigahertz rate, those capacitors are also charging and discharging at a gigahertz rate. And when one capacitor charges, it extracts half CV amount of energy from the source. And when billions of transistors are charging, so you can imagine how much amount of energy is extracted from the source. And similarly, when capacitors are discharging, this amount of energy is being dissipated to the ground. And that is why you have seen today's processors, they have a fan on their top. If you don't use that fan, then if an egg is placed on the top, it turns into omelette. This is very true fact. And to keep these processors in a cool environment, all these air conditionings and fans are required. And today's major concern is therefore to curb leakage power also along with the dynamic power. This is a very popular relation for power consumption in any computing device. You can see there are various factors here. Alpha is a switching activity. F is a frequency. Frequency means cycles per second. If a system has a huge amount of capacitance and if it is switching at a very fast rate in a given amount of time, it will consume large amount of energy. But it has a huge capacitance and then in a same amount of time there are no switchings or very less switchings, there will not be any power consumption.
Hello.
So how many switchings take place within a given amount of time, that is determined by alpha, which is a switching activity.
Excuse me, sir.
Hello?
Hello. Sir, we are not able to see your PowerPoint, sir. Thank you, sir. Thank you, sir.
Sir, refresh your window while pressing F5. Rejoin the call.
So in this power formula, power is equal to alpha, which is a switching activity. Switching activity means within a given amount of time, how many times the processor is switching. It is switching 1000 times or 100 times or 50 times. Less number of switchings means less power consumption. CL is a load capacitance or total amount of capacitance which is connected to the load. Load means which is a fan out of this processor who is working at a gigahertz rate. V is the power supply connected to this, it is volt. And F is the frequency of a processor. For example, it is working at 2 gigahertz rate. So all these factors, they are responsible for power consumption. So from this formula, it is obvious that if you want to reduce the power consumption in a computing device, you can reduce the voltage. If you see the expression, this voltage has a quadratic effect on power consumption. If you reduce V to V by 2, power consumption gets reduced by a factor of 4. Then you can reduce the amount of capacitance which is switching in a given amount of time. You can operate this processor at a lower frequency, but the side effect is when you are reducing the voltage, the performance of the processor reduces. If we eat less food, we will have less energy and our performance will reduce. If we get tired and we don't sleep, our performance will reduce. Similarly, if you reduce the voltage of a processor, its performance reduces. And if you are reducing the frequency also, again it becomes slower and the tasks, they will be taking more amount of time for their completion. So if you want to keep the performance same, but at the same time you want to reduce the power consumption, then what should be done? Instead of using one processor, we'll be using in parallel 2 processors. So amount of activity will be reduced to half. So frequency can be reduced to half because now each processor will be doing 50% job. So F can be reduced in that case and performance will be same. So you can reduce frequency provided you now use the systems in parallel. In that case, you can reduce the voltage also, which has a quadratic effect on power consumption, and you can also reduce the amount of capacitance which is switching, charging or discharging in a given amount of time. These are the various techniques, very popular techniques which are used in the industries for curtailing the power of any computing device. Any device can be seen at various levels. You can see a device in the form of complete system. If you look inside, it is in the form of processors, interconnects and peripherals and buses. If you go further down, you have a gate level design, and if you see more details, it is a transistor level design. So at every hierarchical level, at every abstraction level, there are different techniques for curtailing the power, for reducing the power. As far as transistor based design is concerned, there is only 5% flexibility available for reducing the power, whereas at system level or at processor level, more than 80% flexibility is available for reducing the power consumption of a device. You can see this diagram for various abstraction levels, various power reduction techniques are available. At system level, you have dynamic power management and you have voltage and frequency scaling. At system level, where device has been fabricated, system has been built, and now you cannot change the internal circuitry of the system. So what options is available? You see how the system, when task is given to the system, entire task, if seen in the form of smaller frames, there are some frames which can be executed at a low speed, and other frames they have to be executed at a very fast rate, at a high speed. So when computational requirement is low, at that time you can reduce the performance of a processor by reducing the voltage and by reducing the frequency. And if you reduce the voltage, it has a quadratic effect on power reduction. If you reduce the frequency, again it has a linear effect on power reduction. And when performance requirement is high, you upscale voltage and frequency. So depending upon how much speed is required in a particular slot for a given task, your controller can predict that, and accordingly voltage can be reduced or it can be increased, and also the frequency can be reduced or increased. When you are seeing the architecture level design, at that there are other techniques. Clock gating is there. What is clock gating? Clock gating means in a sequential circuit, every module has to be clocked synchronously, but all those modules which are not working during a particular time, their clock should be blocked. And by blocking the clock, you are straight away saving 50% amount of power. And today, there is a trend, new trend for designing asynchronous processors. Asynchronous means these processors and their peripherals, they are not using the clock. So they are saving straight away 50% amount of energy. We human beings are asynchronous processors. We are not connected. Individuals are not connected to each other through a clock. We are talking to each other using handshaking signals. Same concept is being used now for designing the processors. They will talk to their peripherals not through clock edges. They will talk through handshaking signals, and they will be saving a lot of amount of energy because of clock gating. Power gating is another important concept. Switch off the modules which are not in use. Any computing system has large number of modules, so straight away switch off those modules which are not in use. When you are switching off the module, you are saving dynamic power as well as static power. When you're working with your laptops, when it is active, there is a dynamic power consumption because it is doing calculations at a gigahertz rate. At the same time, some leakage, inherent leakage is taking place. But when your laptop enters into a sleep mode, dynamic power is not there. Only leakage power is taking place. And you might have observed when your laptop is off, is in sleep mode, it gets heated very frequently. That fan works more frequently, switches on more frequently because leakage power in today's processors is much more than dynamic power. It is more dominating component. And when your laptop enters into off state, leakage power, because power has been cut off, VDD is a main region for dynamic and static powers. When VDD is disconnected, dynamic is 0 and static component is also 0. So these are the various techniques available at various abstraction levels, and they have their side effects also. When you're using a particular technique for power reduction, for example, you're using a clock gating or power gating technique, you have to use some additional circuit which is meant for checking which module is not working and its clock should be blocked and its power should be blocked. So that controller leads to increased amount of hardware, and this leads to increased area on a silicon buffer. So this is a penalty. You are trying to reduce a power, but at the same time area is increasing. So, and sometimes efficiency reduces. The controller, which is meant for checking whether power gating is required or not, clock gating is required or not, that controller is also consuming the power. It has to work. It has to remain on. It is always on. So it also consumes power. That is additional penalty. ITRS, International Technology Roadmap for Semiconductors. This has predicted 18 technologies for power reduction which will be lasting up to 2026, and out of these 18 technologies, the most prominent 3 technologies that will be most popular in the industrial world are adaptive body biasing. Adaptive means programmable. You can increase the bias, it can reduce the bias. Power gating, whenever required, whenever any module is off, the controller will be switching off the power of that module. This is power gating. And dynamic voltage and frequency scaling. Dynamic means for a given task, a particular frame can be operated at a slow speed with slow performance. The controller will automatically reduce the voltage, will reduce the frequency. And when it finds that next incoming frame has to be executed at a very fast rate and high performance is desirable, it will increase the voltage, it will increase the frequency. When you are sitting in a class, you are very attentive and your power consumption is large. When you are sitting in a canteen, you are relaxed and your brain is working at a very relaxed rate and power consumption is very small. When you are in a hospital, different amount of energy is required. When you are in a playground, different amount of energy is required. Similarly, the processor entire task can be seen in various frames, and depending upon the requirement, computational requirements, the voltage and frequencies, they can be upscaled or downscaled. So these are those 18 technologies which ITRS has predicted, and out of these technologies, power gating is assumed to be most efficient as far as power reduction is concerned. And now we will be talking about power gating technique. When you are going to employ a power gating technique for reducing the power consumption of a computing device, there are some side effects. One is area penalty, because you have to employ a power gating controller which consumes additional area on silicon buffer, and there may be 5 to 15% increase in that area. There may be a timing penalty because it has to take the decisions for switching on or switching off the power, so there may be 4 to 8% increase in delay. But as far as power saving is concerned, it can help 10 to 50 times reduction in power. Performance, area, and power consumption are 3 vertices of a triangle, and these are the 3 major parameters for which we are doing the optimizations. Your target can be to reduce the power, your target can be to reduce the silicon area, your target can be to enhance the performance. But the problem is when you are trying to optimize one of these three, other two are going beyond the limits. This is the major bottleneck when you are trying to control one of these parameters. This is a general block diagram when power gating is employed in a computing system. There will be a power gating controller who will be looking after the modules which are to be switched off when not in use. There is a module which has to be power gated. There are isolation cells. There is some circuit which works and disconnects the power gated module from rest of the circuit. So, and there is a power switching fabric. We will see taking some example. There are, as far as power gating is concerned, there are two types of concepts: coarse grain power gating and fine grain power gating. When every module has its on-off provision for power, it is called fine grain gating. When all the modules are controlled by a single on-off circuit, it is called coarse grain gating. And there is ultra fine grain power gating. It means the hardware which is meant, there are switches with each module. Switch is not a simple on-off switch, it's a circuit. There are switches with each module for cutting or connecting the power, and that additional hardware is also participating in the functionality of the module. It is very important to understand it. When you are employing a power gating in general, you are adding additional controller, and that leads to increase in hardware, and area on a silicon wafer increases. Whereas if you are using ultra fine grain gating, you are not adding additional hardware. Some part of the entire circuit is helping in power gating, as well as it is participating in the functionality of the circuit. So hardware penalty is minimized or reduced to zero. So this concept is further elaborated. These switches which are enabling or disabling the power, they are called sleep transistors. They force the module into a sleep mode. Another thing is capacitive power dissipation. There are large amount of parasitics associated with the processor, associated with interconnects, and associated with the peripherals which are responsible for power consumption. And if you see a capacitive load, when frequency increases, its charging discharging increases, power consumption increases. Half CV square is a consumption in one cycle. So when large number of cycles are there, large number of half CV squares will be there. Voltage swing is also affects charging and discharging of capacitors, and activity factor in a given time, how many times capacitor has to switch, 0 times or 50 times or 100 times, whatever is the value of clock. But important is how many times it has to switch. That also leads to power consumption. Short circuit power consumption. If you know CMOS inverter, where PMOS and NMOS are used to design inverter, if you give high input, output is low, and vice versa. But when input is having a transition from low to high, when you have a low input, if you remember CMOS inverter, PMOS is connected to VDD, NMOS is connected to ground, and when input is low, PMOS is on, current is flowing from VDD through PMOS and to the capacitor, and capacitor starts charging and finally reaches half CV square. When input is high, VDD is disconnected because PMOS is off. High means NMOS is on, and this half CV square energy dissipates to the ground through NMOS. But when you are going from low to high, PMOS is now going from on state to off state, and NMOS is going from off state to on state. And during this transition, there is a short interval when both the transistors are partially on. One is going to off state, another is going to on state. So there is a small interval when both are on, and because of this, VDD and ground, they are shorted. Between VDD and ground, there is a PMOS and NMOS. And when both are on, there is a short circuit path between VDD and ground, and heavy amount of, you might have seen, if you short circuit positive and negative terminals in your house electricity connections, everything, all the wires will burn, even energy meter will burn, because large amount of current flows. Similarly, when ground and VDD, they are shorted because P and NMOS are simultaneously on, short circuit current flows, and this is also a major component of power consumption. There is a dynamic power consumption when there are switchings, processor is computing. There is a static power consumption. There are leakages in transistors. There is a capacitive power dissipation. There is a short circuit power dissipation when P and N are shorted. There are glitches in the circuits. They are also responsible for power consumptions. What is a glitch? Suppose you have an AND gate with two inputs and their path lengths are different. You have an AND gate and these two inputs are terminating on an AND gate, but these two inputs have different path lengths. One is having R1 C1 parameters, another R2 C2. So R1 C1, if you take tau 1, which is R1 into C1, this tau 1 is different from tau 2. It means these two inputs will take different amount of time to reach at the AND gate. And when this timing differentials are there, when timing mismatch is there in the arrival of these two inputs on a common point, which is a AND gate, unwanted pulses are generated. You are sending 1 and 1 on both the terminals. Output of AND gate should be 1. But because of timing mismatch, one of the inputs has not risen to 1. It is still at 0 and another has reached logic 1. So 1 and 0 leads to 0, whereas expected output is 1. This 0 spike, this negative spike will last for a short interval, but it will charge many capacitors. When there is a spike, it will charge the capacitors or it will discharge the capacitors. This is a glitch, and these are unwanted chargings and dischargings of capacitors and huge amount of energy dissipated. This is one limitation. And second is, these spikes may lead to malfunctioning of subsequent circuits which are being driven by this circuit where glitches are generated. So glitches are also power consuming unwanted events. Whether your circuit means it is made up of transistors, CMOS transistors. Whether your computer is on or in a sleep mode, the transistors are connected to power supply, they are connected to VDD, and therefore leakages, the leakage currents are there. You cannot eliminate those leakages. when transistor is on, there are tunneling effects. Certain hot electrons are tunneling through gate oxide into the substrate. This leads to leakage. Flow of electrons is a current. When there is a current through a resistive path, there is I square R. There is a power dissipation. So when transistor is on, tunneling, leakage current, and many other components are there. So leakages are taking place. When your computer is in sleep mode, transistors are still on, activity is not going on, but transistors are on, and therefore sub-threshold leakage is there. Electrons are flowing through a channel. Flow of electrons is a current. Source to drain flow is there. Drain to body flow is there. You must have a picture of a MOS transistor in your mind. There is a substrate. There are two islands, P-type, N-type, and in between there is a gate which is separated by silicon dioxide insulator. So when transistor is in sleep mode, drain is still sending some electrons towards source, and this is a leakage. There is a tunneling from drain to substrate. This is a leakage. This is a concept of a glitch. AND gate has many inputs, n inputs. First input arrives at time t1, last arrives at tn, and t1 minus tn, first arrival and last arrival, this time difference is there because of mismatched path lengths. These inputs are not having same tau, not having same R and C, because their lengths are different. So these inputs are arriving at different points of time, and because of this differential delay T1 minus Tn, glitches appear at the output of a gate. Di is a inertial delay of a gate. Any semiconductor device, whether it's a diode, transistor, or any device made up of these transistors, they have a propagation delay or inertial delay, because if you see a diode has a inherent resistance, VI characteristic. There is a slope, and this slope means Ohm's law is being obeyed. It means resistance is there, and at the junctions there is a depletion region separated by positive and negative charges. So there is a capacitance. Because of these inherent capacitive and resistive effects, even diode has a propagation delay, and any other device, bigger device made up of diodes is having a delay, and that delay is Di. Inherent delay is Di. If you see this diagram, this says that if differential delay of the inputs, there are two inputs, on one there is a 0 delay, on the second one there is a 2 unit delay. If this differential delay is bigger than the propagation delay of a gate, which is 1 unit shown here, then glitches will be transferred to the output. Glitches will be generated, and they will be visible on the output side, and they will also enter into the subsequent circuits. Whereas if this differential delay is smaller than the inertial delay of a gate, these glitches will be suppressed. These glitches will be suppressed. If this condition is satisfied, differential delay is smaller than the inertial delay, there will not be a glitch. It will be eliminated by the circuit. So what is the remedy based on this? Either you reduce the differential delay of inputs. This can be done by inserting the buffers. If there is a differential delay of 2 units, then I can insert another buffer of 2 unit delay in the second input. So 2 minus 2 is 0. There is no differential delay and no glitch will be there. Or you increase the inertial delay of a gate. This can be done only at a device level. It cannot be done when system has been built or circuit has been designed. If you're working with silicon, P-N type materials and silicon dioxide, at that point inertial delay can be taken care of. Otherwise, the only remedy left is you insert the buffers to balance the delay and to eliminate the glitches. So this is done here. In the smaller diagram, there is a 2-unit difference, whereas when buffer is inserted, it is 0.5 unit difference, and it is smaller than the inertial delay of a gate, so no glitches will be there. This is a adder. Adder, everybody knows, 3 inputs, 2 outputs, sum and carry are the outputs. And this is a transistor level circuit, very popular circuit, and it is taken as a standard circuit in literature. It is made up of transistors, PMOS and NMOS transistors. Now, in this circuit, whenever inputs are changing, they have to travel from one end to the another end to produce sum and carry. And path length between inputs and sum and path length between inputs and carry, they are not same. And that's why this adder produces glitches. You can test it using some EDA tool for example, cadence or Mentor graphics. You will find these glitches, and this is the reason, because these path lengths are different, and therefore sum and carry are generated at different points of time, not simultaneously, and it's a reason for glitches. This is a 4-bit adder where carry in is going from 0 to 1, A is 0, and B is going from 0 to 1. When two inputs are 1 and 1, what is the sum? Sum is 0, carry is 1. Or otherwise, 1 plus 1. Sum is 0, carry is 1. And this is a carry propagation adder. So carry has to propagate from first stage to second stage to third stage to final stage. And this carry and the input B, they are not meeting at the same point of time. So this leads to generation of a glitch. So in the graph, you can see that when S0 is produced, glitch is smaller. When S1, sum S1 is produced, it is amplified much bigger. Then S2 is bigger, S3 is again bigger than S2. So glitches, they travel when number of stages are more. When mismatch is there, glitch is produced. But when glitch has to travel from n number of levels, it will be amplifying and it will be going to the subsequent circuits. It will be charging and discharging the capacitors which are not desirable, chargings and dischargings, and also it may lead to malfunctionings. In a multiplier circuit, there are partial products at the end and they have to be added. Column-wise bits, they have to be added. If there are 4 partial products, then you have only 4 levels. If you have 10 partial products, number of levels are 10. So glitches will propagate from 10 levels in one case through 5 levels in other case, and in bigger multipliers it has to travel many levels. Levels means partial products. So more number of glitches can be seen in bigger multipliers. And it is written here in a 32 by 32 multiplier, 2 operands of size 32 bits, glitch power becomes 60%. Its contribution is 60% as far as power consumption is concerned. In a smaller multiplier, it will be smaller. So it is also very important to find out the glitches and to reduce them to make them 0. Full adder, I am taking an example of full adder for further discussion. Full adder in literature is also called 3:2 counter. 3 inputs, 2 outputs, right? If all the inputs, 3 inputs are 1, 1, 1, output is 1, 1. This output is counting how many bits are in the input, how many bits are high on the input side. If all the 3 bits are high in a full adder input, what is the output? 1, 1. This 1, 1 is saying there are 3 inputs which are high. 1, 0 output says there are only 2 inputs high out of 3 bits. 0, 0 says all the inputs are zeros. So it is counter. It is also named as a counter. 3:2 counter. 3 inputs, 2 outputs. This is a full adder. Everybody knows the truth table. Sum is there and carry is there. Now we want to redesign this full adder so that we are able to use power gating. ITRS has predicted that up to 2026 power gating will be the most efficient power reduction technique. Power gating. Switch off those modules which are not in use. This is power gating. So we'll be using a power gating concept in designing the adder so that it consumes less power. And also we will do something to reduce the glitches in this full adder. So how we will start with the design? We will partition this. Everybody knows the truth table, but now we will see this truth table in 2 sets. All zeros inputs, all high bits inputs forms one set, and rest of the combinations, this is another set. These are 2 sets of inputs. We have partitioned this into 2 sets. If you see, except all zeros and except 1, these inputs versus carry. If you see these inputs, the middle partition and the carry is a majority function of inputs. Again, it is well known, also written in books. It's a majority function of inputs, and this majority function, which is a carry, if you complement this, you will produce some bits for a particular combination. So if you are able to produce carry, then just using inverters, you will be producing the carry. So this much is clear. NAND and NOR gates are universal gates. If you have studied digital electronics, this is always said. NAND and NOR are universal gates. I can ask a question, out of NAND and NOR, which one is faster? Both are universal gates. Everything can be designed using these 2 gates. Which one is faster, NOR or NAND? Which one? Which takes lesser time to produce the output once input is given? So think about it, and I will again ask. Now this is the same truth table shown in a partition form. We will use these inputs as inputs of NAND and NOR gates. We are applying these inputs of a full adder to NAND and NOR gates, and these are the values produced. You can see in the diagram. In case of NAND, starting from LSP, all bits high, and in the last combination, the output is 0. In case of NOR, if you start from bottom to top, all bits are 0 and the only topmost bit is high. This you can easily see and you can easily implement. Now we will use these NAND and NOR gates to produce sum and carry. We will use these NAND gates and NOR gate to produce sum and carry, and this diagram changes to this form. It is a full adder. Now this design, you can see it is shown in 4 segments. Segment number 3 is a circuit, is a NAND and NOR combination where inputs A, B, C are given and NAND output and NOR outputs are produced. This is a block where NAND and NOR gates are there, one NAND and one NOR, and they are producing the outputs as per this truth table. Right? Segment number 4, the NAND input is given to the gate terminals of T1 and T3, and in the same segment the gate terminals which are tied together in T2 and T4 transistors, here NOR is connected, NOR output is connected. Clear? This can be easily done and understood. N1 and N2 are the terminals where sum and carry are produced. And this segment number 4 is meant only, it will be active only when ABC is 0, 0, 0 or 1, 1, 1. You can see the table, this truth table, when ABC is 0, 0, all 3 bits are zeros, NAND and NOR are producing 1, 1. Right? When ABC are 1, 1, 1, the last combination, NAND and NOR both are producing 0, 0. And now you see this. When, take the first combination, all zeros. When NAND is connected here to the tied gates of T1 and T3 and NAND is producing 1, T1 and T3 are off because it should be 0 for these transistors to be on. Yes or no? Are you able to see the diagram? T1 and T3, when NAND output is given to their gates, NAND output for all zeros is 1, T1 and T3 are off. And NOR output is given to T2 and T4, these transistors are on. And what is the output? These transistors T2 and T3 are on and they are connected to ground. When they are on, sum is grounded and carry is also grounded. Right? And what is the output? Sum should be 0 and carry should be 0. Similarly, when all the 3 inputs are 1, 1, 1, NAND is producing 0. So in segment 4, T1 and T3 are on, and the sum and carry capacitors are directly connected to VDD and they are charging. They are going to 1 and 1. T2 and T3 are off because NOR gate is producing 0. T2 and T4 are off. So now sum is 1 and carry is 1. So this segment number 4 is responsible producing sum and carry when all the inputs are zeros or ones. For all other combinations, segment number 1 is responsible for producing carry and sum values at terminal N2 and N1. Right? You see segment number 2. Segment number 2. Here NOR output is connected to the PMOS transistor and NAND output is connected to NMOS transistor. Right? For all other combinations except all zeros and all high bits, what are the outputs of NAND and NOR? You can see this truth table. NAND is always 1, NOR is always 0 for a middle partition. And when this is there, NAND is always 1, NOR is always 0. So PMOS is always on, NMOS is always off. It means VDD is disconnected. Either you disconnect VDD part or disconnect ground part, that supply path is broken. And this is power gating. This is power gating. NMOS is 1, NAND gate is 1, NOR gate is producing 0. Yes, for this middle partition, NOR is producing 0, PMOS is on. For middle partition, which is a majority function, NOR is 0, PMOS is on. NAND is producing 1, NAND is producing 0, so this is NAND is producing 1, so this is also on. For middle partition, PMOS and NMOS both are on, so power is there. This majority function, segment number 1 is working. It is connected to power. Ground is connected, VDD is connected, and it is working fine. Whereas when all the inputs of NAND are same and all the inputs of NOR are same, either they are 1 1 or they are 0 0, and when this 1 1 or 0 0 is given to segment number 2, PMOS and NMOS, there is a disconnection either at ground or either at VDD, so it is disconnected. I mean to say that when this segment number 1 is not working, we are disconnecting it from VDD supply. We are breaking the path of VDD and ground, so it is switched off. And when this module is working, its power is connected. And if you see segment number 4, when the inputs are other than all zeros or all high bits, either T1, T3 are off or T2, T4 are off, and here power is disconnected. So this is power gating. It's a full adder circuit. It is doing power gating. We are not using additional controller here, and this entire circuit, all modules are participating in the functionality. So this is ultra fine grain gating. And we can compare this with a general block diagram. There's a power gating controller. Segment number 2 is a switching fabric. Segment number 3, which is producing NAND and NOR outputs, is a power gating controller. Segment number 4 is always, this is segment number 3, power controller here and power controller there. This is segment number 1, and here in the block diagram it's a power gated block. When not functional, power is off. And this is always on block. So we are able to design a adder where power gating has been implemented without adding additional hardware. We are switching off those circuits which are not in use, so we are saving the power. We have designed this circuit, we have tested this circuit on Cadence, and we have published paper on this. This is a new circuit. So ultra fine grain power gating. In this circuit, controller is a part of circuit. It is a functional part of a circuit, nothing additional is used. This power gating controller has a dual role. It controls the module's power for on-off operations, and it also participates in the functionality of the circuit. So everything is a part of the circuit. It is controller as well as module or sub-module of a circuit. This is a short circuit. When PMOS and NMOS are simultaneously on, when your input is transiting from 0 to 1 or 1 to 0, out of these two transistors, one will be going to on state, another will be going to off state. So during this slope, this is 0, there is a slope and then 1. So during this slope, there is a window, small window, when P and NMOS are on, and there is a short circuit between VDD and ground, and it leads to huge amount of power dissipation. And in this circuit, in this adder circuit, we have avoided short circuit also. You have not seen any book where short circuit has been avoided. By making the circuits faster, by making PMOS and MOS faster, that window can be reduced so that short circuit interval is reduced. But it is not eliminated, and this is not done in any earlier research or paper or book. In this case, we have been able to reduce the short circuit to 0. We have completely eliminated the short circuit. How we have eliminated? We have created a phase shift between PMOS and NMOS operations. That window has been partitioned. That window that has been partitioned, and when PMOS is on, NMOS is not on, or vice versa. During that window, which is undesirable, only during that window, both are not on simultaneously, and short circuit is avoided. And you can see this in this diagram. This is a diagram of segment 4, where NAND gate output is connected to the gate terminals of T1, T3. NOR gate output is connected to the gate terminals of T2 and T3. This is elaborated again. Clear? This is clear. And now this is the diagram which shows. If you remember the circuits of NAND and NOR, in case of NAND, at the ground terminal there are 2 transistors in series, and at VDD side 2 transistors in parallel. Parallel transistors have a smaller resistance. Series resistance has a bigger resistance. In this gate, when capacitor is being charged, in case of NAND gate, when you are going from 0 to 1 transition, means initially capacitor was discharged, now we are charging it through VDD. So those parallel transistors are switched on and ground transistors are switched off. Because of this parallel resistance, 0 to 1 transition is faster than 1 to 0 transition. If you see NOR gate, in a NOR gate, ground transistors are in parallel, upper transistors are in series. So when you are charging the capacitor through a NOR gate, it is slower because it's a bigger resistance, then slower than when you are grounding it, because at the ground the transistors are in parallel, so you can ground it immediately. So 1 to 0 transition is faster in NOR. I was asking, out of NAND and NOR, which one is faster? The answer is, when we are considering 1 to 0 transition, NOR is faster because of those parallel combination of the ground, and when it is a 0 to 1 transition, NAND is faster. This is the answer. And we have used this feature for time shifting that window where P and NMOS are simultaneously on. If you see this diagram, we are taking ABC equal to 1, 1, 1. ABC equal to 1, 1, 1. Initially, you see the lower diagram, initially input is 0, all zeros, and then it is going to 1, 1, 1. All the inputs are transiting from 0 to 1. Now you see the upper diagram, it is with reference to this circuit. You see the upper diagram, it is, you see the 1 to 0 transition. In 1 to 0 transition, NOR gate is transiting faster. In case of NOR gate, 1 to 0 transition is taking place earlier, and in case of NAND gate, 1 to 0 transition is taking later on. because of those parallel and series combinations, right? So there is a delay introduced between NAND transition and NOR transition. NAND output is reaching 0 later and NOR output is reaching 0 from high earlier. So that window is avoided. And finally both are 0, 0. Our input is going from 0 to 1, so output should finally go from 1 to 0. Finally it's alright, but we have been able to avoid that simultaneous on of P and NMOS. And when you see on the input side, when there is a 1 to 0 transition, all three inputs 1, 1, 1 are now toggling to 0, 0, 0. So output should go from 0 to 1. And when it is 0 to 1 transition at the output, you can see the diagram again. NOR gate transition from 0 to 1 is slower, so it is taking place later on. Whereas 0 to 1 transition in case of NAND gate is faster, so it is taking place earlier. So again, that window where PMOS and NMOS are simultaneously on, we have divided this. We have shifted this on-off simultaneously on operations, and short circuit is avoided. This is also a new research. We have tested it, we have published it, and now short circuit can be reduced to 0. So this component, which is very huge amount of power consumption, and earlier it was said that it can be reduced but cannot be eliminated. Now we can eliminate it, so short circuit can be avoided. So this was about power gating and short circuit avoid, how to avoid short circuit and how to introduce power gating. We can stop for a
We can call queries.
queries. Yes. Any question from your side?
First of all, we can ask queries from the site.
Please ask the questions. Other centers may ask the questions. Any doubt in this discussion?
Hello.
Yes, please.
So this was a very nice lecture. Myself, Dr. Vaneet Singh from Gurudev Bahadur Institute of Technology, New Delhi.
Right.
Sir, there is one question. There are various approaches to measure the power dissipation, like at microprocessor level or board level, transistor level, and cell level. So, which one we should go for? That one is accurate out of the three approaches. Which one you feel that one is the best one?
Now, you want to reduce the power or you want to measure the power?
Measurement of the power.
Measurement. There are EDA tools available and there are modules available in them. Xilinx also has a X power tool. Cadence is also having a provision for computing currents in different modules. So V into I can be computed.
So out of these three approaches, which one we should go for that gives me the accurate power level?
Which three approaches you are talking about?
At the microprocessor level or board level or transistor level or at cell level. So out of three, which one should I go?
If you are using Cadence and Mentor graphics, then it's a transistor level design where power measurement will be done.
Okay.
If it is a processor level design, then you do not have any access to transistors, so other available methods can be used. If you are writing RTL code and doing something on FPGAs, then X power is a tool available with Xilinx which can be used for measurement. So depending upon your abstraction level, whether at microprocessor level, RTL level or transistor level, different approaches are available. So we cannot say which one is better and which one.
This approach is the best one.
No. Again, I'm saying that when you're working with microprocessors, you cannot use that approach which is useful at transistor level. When you're working with FPGAs, you cannot use the approach which is useful at transistor level or useful at microprocessor level.
Right. Thank you.
Any other question, please?
biasing, right? I think this is something in which can be done at a transistor level.
Yes.
So, okay. So when and we talked about that no system level thing. So in that system level thing, can I go for adaptive body biasing? And if yes, then how much power distribution I will be saving on power distribution if I go with adaptive body biasing along with other things? Is that a possibility?
Yes, there is a possibility. I can show you a slide. You can see just below the power shutoff, power gating option is encircled. Below that, you have adaptive voltage option is also there. Your leakage current can be saved 2 to 3 times or 2 to 3%. Leakage power reduction 2 to 3% is feasible. Dynamic power 40 to 70% is feasible. If you see power gating here, almost 0% possibility is there for saving dynamic power. Whereas in adaptive voltage biasing, AVS, you have 40 to 70% saving of power.
Yes, so the question was like, what if we are doing ABS and we are doing NFS, and if we are talking about particularly of lower technology, like 45 nanometer, where my leakage is the main concern. So I think it is my assumption that I will be getting a better power reduction if I be effective body biasing.
No, you want to know which one is better, DVFS or adaptive body biasing. Am I right?
Yes, sir.
As far as
System level, what I just want to understand that if I am working at a lower technology board and I am doing adaptive body biasing, right? And at the system level, I am doing some kind of saving. So which is going to save me more? Whether it's going to be adaptive body biasing or it's on a system level, power saving which I am doing at the system level.
please repeat your question. You are working at a board level.
Yes, I'm saying that I'm having at the end of the day, all I'm having is a circuit level, right? So my question is that if I'm keeping the adaptive body biasing, right, and your technology node, that is considered as 45 nanometer. So will I be saving more using adaptive body biasing? And if yes, then by how much?
No, if it is DVFS, it is a different scenario. In case of DVFS, you are saving dynamic voltage. You are saving dynamic power consumption. As far as adaptive biasing concerned, it has different set of advantages. You cannot say out of these two which one is better and which is not better. Again, depends upon your concern, whether you are concerned for saving switchings inside the circuit or you are not concerned about.
Actually, my concern is that I'm using a low technology node and I'm saving some power and doing power consumption at system level, right? And another, I'm saving some power at my internal transistor level using electric body biasing. So which will give me more power saving?
At a system level, power saving is better. I have already said that as abstraction level, you are going from system to a transistor level or a device level, flexibility of saving the power reduces. Right? At a transistor level, only 5%, about 5% chance flexibility is available to you, whereas as you go higher, it goes 40%, 60%, and 80%. And you have a best flexibility available and more chances for better power saving at a system level. Anything else, please?
More queries from friends. So I think we can wind up here and session for
Thank you very much.
15 minutes. Timing, 50 minutes.
Okay. So thank you so much, Dr. R.K. Sharma. And it's time for the tea break, and we will gather here at 11:50 for after 15 minutes. So thank you.
हाँ हमको भी सीखना यार कैसे यूज करते हैं। हाँ नहीं तो कैसे गूगल गूगल प्लस क्या
जो मोबाइल में है तो उसमें रहता है आजकल।
हाँ मतलब कौन सा गूगल प्लस में या
ये वो
ओके वो लगवाना है। हाँ, अगर वो हो जाएगा तो ये ओके कर देगा।
वीडियो कॉल कर देंगे और जिसको भी कॉल करना है।
नहीं तो फिर लॉगिन मांगता है।
आप लॉगिन आपको लॉगिन
गूगल में तो हमेशा ही लॉगिन करता है ना मोबाइल में।
जीमेल लॉगिन करना होगा।
जीमेल तो हमेशा ही ऑन रहेगा, नहीं तो एंड्रॉइड काम कैसे करेगा। ये तो स्मार्टफोन का बेसिक्स है।
इसका जीमेल पे जो भी आता है
वो हमारा 2 दिन से आया नहीं ना, हम इसीलिए तुमसे पूछे कि मेरा ऑटोमेटिक आता रहता था और हमारा ये 2 तारीख के बाद से कोई मेल आया नहीं इसमें मोबाइल में। हमें कॉल करना है हमारे नंबर पे। सेव करना जरूरी है क्या?
ये सिर्फ मेल आईडी होती है ना, आपका मेल आईडी तो होगा।
क्या मतलब जैसे हमको अगर शगुन को करना होगा तो शगुन को मेल आईडी पे करेंगे।
प्लस का है ना ऑप्शन
या तो वो इसका
और टीचर बहुत प्रोडक्टिव है। जाना जरूरी है, संस्थान में जाओ आप फेस टू फेस बैठो तभी सही होता है। इसमें तो कितना सारा है वरना सामने है स्क्रीन ऊपर लैपटॉप
सुनिए
कभी करोगे तो गड़बड़ा जाएगा।
हेलो हाँ वो कॉल में ट्राई कर रहा था उसका ना क्या नाम है अकाउंट पे। हाँ चली गई। हाँ देख
ITRC याद है कई है यहाँ पे सिक्योर्ड विद ये है
ITRC होगा जिसमें आपको नहीं चाहिए
पासवर्ड ये बात है इसमें ये भी तो है
हम लोग
देखने का पावर नहीं होनी पल्ले के ऊपर आए
सर आप यहाँ आ जाइए। नहीं
पीपीटी भी खोल देना सर कि वो सेटिंग
सर खोलिए। So good afternoon. We are going to start our second session of the day, which will be on Verilog based VLSI design, and it is again taken by Dr. R.K. Sharma. Dr. R.K. Sharma, please, over to you.
Now in the second part of discussion, we will be talking about circuit design using HDL languages, hardware description languages. For designing a ASIC, this flow is also very interesting, and it is preferred in most of the cases when you're working with FPGAs and all those things. VHDL or Verilog are two options available to us. The only difference in these two languages is, otherwise it's a matter of choice, Verilog is growing from transistor level toward the system level, whereas VHDL is growing from system level towards transistor level. At present, VHDL cannot handle transistor level design, whereas Verilog can handle it. This is an approach for designing a processors. Everything is made up of transistors, and then transistors are combined together to form gates. On one side, you can have combination circuits using gates. On other side, cross-coupled gates, they lead to flip-flops and sequential circuits. And then these combinational and sequential circuits can be combined to form processors. Processors, any processor, any controller, any computing device can be seen in two parts. Whether it is a customized electronic circuit used in household appliances, or any electronic circuit used in aeroplanes for controlling so many parameters, humidity, temperature, pressure, and all other things. Any computing device can be seen and has to be seen by electronics engineers in two parts. One is data path, another is the controller. Data path, which is meant for executing the instructions, which is meant for producing the results. It is a group of interconnects, processors, decoders, encoders, and all those things, and memory devices connected to it. Controller is getting the feedbacks from the data path and giving suitable control signals, issuing suitable control signals to this data path. Human being is also a sequential machine. Any real-time system has to be a sequential machine. Any real-time system, any customized controller has to be a sequential machine. And our system, our sequential machine, can also be seen as a controller here, and hands, legs, eyes, ears as data path. Our hands, eyes, they are getting the control signals from the controller and then doing the appropriate activities. And when a link is disconnected between the controller and hands because of the deficiency of dopamine in brain, it leads to Parkinson. When hands are not under the control of brain, even voice is not under the control of brain. So that is the importance of a controller. In an aeroplane, there are various types of systems, subsystems used, and then everything is under the control of that electronic controller. And all these controllers, they have to be designed in such a way that if anything wrong is going to happen, they should alarm the signal. They should give some message in advance so that some appropriate actions may be taken in advance. If a controller in your mobile phone starts misbehaving and it disrupts your communication, it irritates, but it is tolerable irritation. But if a controller in an aeroplane, when it is flying at thousands of kilometers height, if it starts misbehaving, then it will lead to very fatal consequences. So it is a duty of every electronic engineer to design the controllers which are very reliable, very smart. They have to be fault tolerant, and they should work, they should be able to work in worst environmental conditions. And whenever we are going to design these controllers or these sequential machines which will be controlling many other things, they have to be designed using FSM approach, finite state machine. Any controller can be seen as a finite state machine. And to start with, we can draw its state diagram, and then we are given a definition. We are given some objectives for the controller. So from this set of specifications, we are designing a state diagram. From the state diagram, we have to design state transition table. State diagram means it is able to shift from one state to another state. Our brain is shifting from one state to another state. Similarly, that state machine is going from one state to another, happy mode to angry mode to sad mode to happy mode. These are the states. Similarly, these controllers, they are moving from one state to another state, and under certain conditions, these transitions are taking place. So, we have to know the behavior of state transitions, under what conditions they are moving from one state to another state. And then we have to know what output is produced in a particular state. So we have to write state transition tables, we have to write output tables, and then if required, we have to remove the redundant states. Additional states means additional hardware on a silicon wafer. Complex state machine means a complex circuit on a silicon wafer. And complex circuits, they will consume more amount of power. They will consume more amount of area. So we have to simplify the state diagram, less optimum number of states, optimum circuitry connected with the flip-flops, gates, and all those things. And it will be having more number of switchings, capacitor charging and dischargings, so more amount of heating, and all these things, they have to be tackled by optimizing the number of states, by optimizing the additional hardware which is connecting the memories and all other things together, so that minimum silicon area is consumed, performance is better, and less power is consumed by the circuit. Design time is very small, and debugging is also very easy. All these things can be done only if you simplify the things. And in digital circuits, we have K-maps, we have QM methods to minimize the number of inputs, minimize the hardware circuitry required, and all of the things. This is working.
This is working.
For example, think of a simplest circuit. You're asked to design a 2's complement circuit. How we perform 2's complement? One is complement the bits and add 1 to the LSB, it is 2's complement. Second is, if it is a serial 2's complementary circuit, you are given a binary string, start from least significant bit. All least significant zeros and first high bit, they are not complemented. The rest of the bits are complemented. This is a 2's the final answer will be a 2's complement. Now this is given, this statement is given, design a serial complementer using the second definition and then show the circuit. We do not know the answer, but we know the approach how to design. This is a sequential circuit. Serial 2's complementer is also a sequential circuit. So how we proceed? This is working. Suppose you are given a binary number and then you are asked to design its 2's circuit which performs a 2's complement. So what is its 2's complement? If you see this binary string, the least significant zeros and first high bit, they are not complemented, whereas rest of the bits 1 changes to 0 and 0 changes to 1. So now we can say that this part is just a copy and this part is 1's complement. Now how many states can be there? There will be 2 states in the circuit. One is the copy state and another is 1's complement state. It is working in 2 states. Now in copy state, if circuit encounters any 0 to start with, least significant 0, this 0 is not complemented and output is 0. 0 remains 0. And then as soon as 1 is encountered, it is first high bit, it moves from copy state to 1's complement state and this 1 changes to, this 1 remains 1, but once you are in this state, 0 changes to 1 and 1 changes to 0. Nothing is done. 0 remains 0, 1 remains 1, but as soon as first high bit is encountered, state changes. You are going from copy to 1's complement state, and in that state, any 0 will change to 1, 1 will change to 0. So this is the definition given to us, and from this definition we have produced the state diagram. Now from this state diagram, we will write 2 tables, state transition table and output table. This is present state and this is the input. Or we can take on this side. Present state, copy state means 0, this state means 1. If you are in 0 state, which is copy state, and 0 is the input, what is the state? This is a state transition table. If 0 is encountered, circuit remains in the same state. So same state is retained, 0 is 0. If in the present state 0, 1 is encountered, it moves to state or 1's complement state, and its binary code is 1. And when you are in 1 state, which is a 1's complement state, and then 0 is encountered, 0 changes to 1, but state remains the same. You are in the same state, and when 1 is encountered, again you are in the same state. Right? And output table in a state 0, when 0 is encountered, what is output? 0. And when 1 is output encountered, what is output? 1. In this 1 state, which is 1's complement state, if 0 is encountered, it changes to 1 and 1 changes to 0. This is a small K map. What is the equation? What is the output Z? If you see this table, it is exclusive or operation of P and X. X is input, P is the present state. And now how to write Boolean equations for state transition table. Whenever you are going to solve a state transition table, you must first decide which flip-flop you are going to use. In a state machine, this is a total processor seen in two parts. One is controller, another is data path, and controller is having three important states. This is true for all those controllers you will be designing. What are those three parts? One is next state logic, state transition logic. It's a next state. If present state is given, what is the new state? And this will be written with the help of this state transition table. Output logic. This will be obtained with the help of output table. We are taking a simplest example, so equations are very simple. And state memory. Any controller, whether it is our brain or any other controller designed by us, it will include memory elements to remember the past history, to remember the present state, to remember the inputs. If this is a present state, this is the input, what is the new state? So these are the three important parts in any controller: next state decoder, output decoder, and memory elements. So when you are going to solve state transition table, you must be sure I am going to use T flip-flop or JK flip-flop or RS flip-flop or D flip-flop. Let us decide that we are going to use SR flip-flop for this state transition table. Finally, it has to be translated into a circuit. So there are 8 combinations. These are 8 combinations. We have decided that we will be using SR flip-flop as a memory element. If there are 2 states, one memory element is enough. Because for 2 states, you will be giving 2 codes, 0 and 1. If you have 8 states, then 8 is 2 raised to power 3. So 3 flip-flops are enough. And you will be giving how many bits code? 3-bit code. 3-bit code. 0, 0, 0 to 1, 1, 1. Right? If there are 8 states, if there are 8 states, if there are 5 states, again 3-bit code or 3 flip-flops. So here we have 2 states, so only 1 flip-flop is enough, and that flip-flop is SR flip-flop. Now, if these two, we are talking about truth table of SR flip-flop. If this is 0, 0 and present state is 0, Q terminal is 0, it remains 0, it remains 1. If reset is active, 0 remains 0 and 1 changes to 0. If set is active, then 0 changes to 1 and 1 remains 1, and these two are not, they are not desired, they lead to a race condition. Now let us draw a K-map present state is 0. See this table. Present state is 0, next state is 0. Now which are the combinations where 0 changes to 0? And this combination, 0 goes to 0. Present state is 0, next state is 0. Right? And for these two combinations, SR is 0, 0 here and it is 0, 1 here. So we can say S is 0, R is X, don't care. S is 0 and it is, don't care. This is a first cell. This is for S terminal and this is for R terminal. We have to connect 2 circuits. We must have 2 circuits, one for controlling S, one for controlling R. So this is a table which will be giving Boolean equation for S, and this table giving Boolean equation for R. Now here you are going from 0 to 1. So find out the combinations where there is 0 to 1 transition. This is the only transition from 0 to 1. And this says S should be 1, R should be 0. Right? Now 1 to 1. This is 1 to 1 and this is 1 to 1. 0, 0 here. 1, 0 here. So don't care here and 0 here. And then again 1 to 1, same thing. Don't care here and 0 here. From state diagram, we wrote state transition table. From state transition table, after deciding the flip-flop, we developed K-maps for S terminal of flip-flop and R terminal of a flip-flop. Now from this, what is the equation for S? X. So this leads to S equal to X, and this leads to R equal to 0. We started with a definition of a circuit. We were not knowing the answer. From definition, we wrote state diagram. Then from there, state transition table, and then output table. We decided the flip-flop. We must know the truth table of a flip-flop. Output table gives you equation for output, or it's an output decoder in a controller. This table gives you the Boolean equations, and we can develop the input decoder, next state decoder from these equations. So what is the final circuit? We have a binary string stored in this register. This is a register where initial number is stored. This is the X value. Each output coming out is X. This is a shift register. Now what is the AND? We are using one SR flip-flop. R has to be grounded. This equation says S should be connected to X. And output is exclusive OR operation of present state, means Q terminal, and X. And we can connect this back to this shift register so that answer is obtained at the same place, right? And this is a clock which is common to these two sequential components. So simple. Any controller can be developed using this approach. And if you follow this approach, you need not remember the answers. In BTech, MTech classes, we are in the habit of knowing the answer, and then only then we can solve the problem. Give me the answer, then I will solve the problem. And so long as I am not touching the answer, I will try it again and again. In real-time scenario, we encounter the problems where answers are not available. Similarly, when you're going to design a controller for a given purpose, answer is not available. Some customer will be giving you the problem, giving you the specifications for the controller. You have to design the controller, most optimized controller, most power efficient controller, most reliable controller, without knowing the answer in advance. If you're asked to produce a bicycle, you have to produce a bicycle. If you're asked to design a motorcycle, and then you end up with a only cycle. You were asked to design a motorcycle and you produced a cycle. You are a bad designer. You are a bad designer. And this is the approach true for all types of controllers. And you are the best engineer. If you are electronics engineer, you will be the best if you are able to design most efficient controllers. Our majority of activities are to design controllers. Controller for some electronic circuit, controller for a lathe machine, controller for aeroplane, controller for some automation of rice mills, automation of poultry farms, automation of cold storage units. Wherever you are required to develop controllers. And controllers are real-time systems. They include next state logic. These two tables, they give you next state logic. You require a output logic, output decoder. So this output table gives you output logic, Boolean equation. And you require some memory elements that you can decide SR or T or JK, but you must know their truth tables. This much is required, and if you practice this approach, any type of controller can be designed. So you will be a successful engineer. Don't wait for answers. Don't wait for copy-paste type of things. So this is clear. State machine has 6 tuples, It's a set of X, Z, S. X is input, Z is output. S is a state space. How many states are there in a sequential machine? S naught is a reset state. Delta, it's a function of X and S and gives you the next state. If current state is known and inputs are known, what is the next state? And lambda, if current state is known and inputs are known, what is the output? Right? And there are two options, Mealy machine and Murray machine. If output is a combination of inputs as well as current state, it is a Mealy machine. And if output is only a function of current state, it is a Murray machine. So you can design both ways. They have different advantages in different applications in terms of speed, in terms of hardware. So controllers can be designed using one of these two approaches, Mealy or Murray. People today, they are writing state diagrams for brain, human brain. They are writing state diagrams for hand movement. They are writing they are drawing state machines for pollution control. They are writing state machines for water management system, transport system. So this theory, it's everywhere you require a real-time controller, real-time supervisor. When you are in a car, you are the controller. And car is a data path. Your brain is going to decide which way to turn the steering wheel. And when you are writing a transfer function for the system, car and a driver, that driver is also a part of transfer function. And you can find what happens if that driver is not, that controller is, if controller in a car, driver in a car is not behaving properly, then what happens to the car? And what happens to the passengers who are sitting with that controller? If that driver is intoxicated and he is driving a car, what happens to the car? So controller has to be perfectly designed, reliably designed, efficiently designed, and it should be optimized all the three parameters: power consumption, performance, and area. This is a problem, another problem. We are asked to design a circuit. We are given only definition. We are not given answers. We are asked to design a circuit which has three inputs, S, X, and reset. You know what is reset and what is clock? And two outputs, P and L. When S is high and X is inactive, P produces one pulse. And L is a replica of S. When S is high and X is high, P produces train of pulses. At every clock edge, it should produce a pulse. This is a problem. So we have to design a solution. So how we proceed? First, we start with a state diagram. Initially, P and L both are inactive. So P bar, L bar, this is the first state. In the next clock edge, when clock goes high and S is also high, we have switched on S. So S is high, and then when clock edge goes high, P bar changes This is if I going back to first and so next
Hello, hello. Sir, your voice is not clear here in Madam Malviya University of Technology. Hang हो गया चलो
so the so that is right and if and then it's
Now, if you understand this algorithm, can you tell me what hardware components are required if you asked to design the circuit? Given this algorithm, if you directly start working with hardware design, what hardware components are required to develop the data path? The path which will be processing this algorithm. X after the X plus 1, either I equal to I plus 1, either it can be either, it can be counted. Then I less than equal to 10 is one counted, X less than 0 is another counted. What else? X, Y, and I will have to be stored. So I require 3 shift constraints. So I require 2 computers, 2 others, 3 shift constraints, and then we have to interconnect them. This is another exercise, how to interconnect them so that this functionality is achieved. Processing is a controller, middle part is a data path. So you can see this. One part is processing I plus 1 is performed by other, and this again stored in our I is equal to I plus 1. It is stored in our system. Again, it is given to the other.
So new I plus 1 is performed and updated value is stored in I register. So this is going on until I reaches 10. It is compared with 10. On the other side, X and Y are added with the help of adder, and X is always getting updated value, X equal to X plus Y. And then finally, after 10 iterations, it is compared with 0 to find out whether it is less than 0 or not less than 0. So again, it is very easy to understand if you see the solution directly. When solution is available, everything is nice and we appreciate it, yes, we have understood it. But if solution is not given and then you are asked to develop V is equal to IR relation, it is very difficult. You have seen pictures in theaters, for example, a Sholay. You saw it in 3 hours and it was highly appreciated. You told story in brief to your friend in 5 minutes and he also ran to the cinema hall, right? But the director, he took 9 years to design it, to write a script, photography and all those things. He's the real designer, right? So that should be the approach. You are the designer. Think of a solution. You are not given anything. Think of a solution, think of state diagrams, think of data path, think of the controller. Now these X, Y and I registers, they have to be loaded. So they require load terminal and they have to be cleared at certain point of time. They require clear terminals. So X clear, Y clear and I clear, X load, Y load and I load terminals are there. These load and clear signals are issued by the finite state machine. It is supervising, it is controlling, and it is getting the feedback from the hardware, which is a data path, X less than 10 or I less than equal to X less than 0 and I less than equal to 10. And clock and reset are also, right? So now it's very clear. Suppose there's a problem to convert serial data to parallel data. It's very common phenomenon in electronics designs. Your computer is sending data on RS-232 link serially in asynchronous format. You know what is asynchronous? Every message is sent in the form of a frame where first bit is start bit, then message bits, then parity bits, and then stop bits. This is an asynchronous format for every message. Your data is flowing serially, and at the other end we have to receive it and we have to change this to parallel form. This is the problem. And you are asked to design a solution for this. Can you think of? Most of the students, they say that use SIPO register, serial in, parallel out. But this activity has to be controlled. Initially there is a start bit, it has to be tested. There are 8 or 7 or 6 message bits. They have to be separated from this frame. And then we have to count the parity bits, stop bits, and then one frame is over. All these things, they have to be monitored. Message bits, they have to be separated and saved in a register. So who will be controlling these activities? Controller. There will be a controller, there will be a hardware. Controller will be supervising these activities. Controller will sense the incoming start bit. If it is 0, it will immediately do something. It will enable the register. And register and counters are clock enabled. And then data starts entering. So long as start bit has not arrived, it is waiting for the start bit. And then when 8 bits have been saved in some other register parallelly, it is informed about that. And when everything has been counted up to the stop bit, again it is informed, and then new frame starts. This is a processor here. Controller is also shown separately. RS32 is connected to SIPO. There is a counter and there is an input register here which will receive the data in parallel. Controller is testing the start SD line for start bit. Controller is testing for the start bit, and before that, before start bit arrives, SIPO is cleared and counter is cleared. As soon as start bit arrives, SIPO is enabled and counter is enabled, and they are also connected to data clock, so data starts entering. Enabled means their input doors are open for the incoming data, so data starts entering. As soon as 8 bits have entered into SIPO, counter is sending the signal data over. It is sending the signal data over to the controller. How it will send? When it has counted 8. Suppose this is the number. At this point, we should send a message to the controller that message bits have been counted. So I will end them, and this message will be going as a data over message to the controller. As soon as this count is there, end will produce 1 and it will be given to the controller. It knows data has been counted and it is in SIPO. It will immediately enable FCW register. It is a frequency word for some other application. It is parallel in, parallel out register, and it is enabled immediately, and SIPO content goes to this register, and then enable is deactivated. And then when everything has been counted, parity and stop bits, counter again issues all over. Suppose there are 12 bits. So when count 1100 is there, again this end operation is performed and this output is given to controller, means everything is over. So next frame starts. Again solution is there, so it's very easy. Otherwise students take many hours to design this hardware. And now this, if this is available to you, you can draw a state diagram for this. For the controller, for example, from the state diagram, you can draw state transition table, output table, you can write Boolean equations if memory element is known, and finally that hardware can be designed, and finally the ASIC for that hardware can be implemented using transistors. Or another approach is state diagram is known, write a FPGA code for this, write a HDL code for this, right? This will be the behavior coding of this behavior. It is called behavior modeling. If you are writing the Boolean equations and then writing a VHDL or Verilog code for this, this is called data flow modeling. Using Boolean equations, if you are designing the overall circuit where pin-to-pin connections are shown, flip-flops are shown, terminals are properly connected, and then you are writing HDL code for this, this is called structural modeling. So when you are working with HDL languages, you have 3 options: behavior coding, data flow coding or modeling, and structural modeling. And then you will synthesize the circuit, you will retest it, you will test its functionality, and then you will produce a netlist out of it, and finally again this path also leads to the ASIC design. You can design ASIC for that. This is a controller for serial to parallel conversion. In state S0, controller is waiting for start bit to be 0. So long as start bit is 1, it is waiting. It has to be 0. And during this period, when it is waiting in state S0, it is resetting the SIPO register and resetting the counter. These two activities are done. Now, movement from S0 to S1, this is a straight transition. This is enabled as soon as start bit is 0. As soon as start bit is tested to be 0, it enters into a new state S1, and what is done in state S1? It is enabling the SIPO register. It is enabling the SIPO register. And then once it is enabled, with every clock edge, data is entering into this. And then here controller is waiting for data over message, whether all the 8 bits have been entered or still the process is going on. So long as data over is not active, it is waiting, assuming that the bits are entering into the shift register, and as soon as data over is 1, it means all the bits are inside the register, it goes to the next state. Clear? In the next state now, it is waiting for all over, means everything is over. This frame is over. So long as it is 0, it is waiting, and as soon as it is 1, it is going back. So we have translated the behavior of controller in terms of state diagram, and then from here I can write a code for this. I can download this onto FPGA in the form of bit stream, and then my FPGA will start working in the form of controller. FPGA, there are various FPGAs available in the market. SRAM FPGAs, anti-fuse FPGAs. Any other FPGA? These are the two main FPGAs. Do you know FPGAs? FPGAs are reconfigurable devices. Reconfigurable means depending upon the inputs or depending upon the requirements, it will change. It can change its behavior. As soon as you are sending a new bit stream into the FPGA, counter is behaving in a new fashion, or controller gets updated and it is working in an updated fashion. And then again, if you modify the bit stream, if you modify the code, simulate it, synthesize it, and bit stream is modified, so that controller will again be modified. It is reconfigurable. If you have a floating point multiplier, it can work as a single precision multiplier or double precision multiplier, and it can be designed as a reconfigurable multiplier. Depending upon the requirements, I can ask it to work as a single precision multiplier or double precision multiplier. I am a reconfigurable system. Inside a class I am teaching, I have a different role. When I am with my friends, I have a different role. When I am in home and talking to my children, I have a different role. When I am in a society, I have a different role. So we are also reconfigurable systems. We are changing our modes. We are changing our activities in different scenarios. Anti-fuse FPGAs are one-time programmable FPGAs. SRAM FPGAs can be programmed anytime. SRAM FPGAs cannot be used in space applications. They are attacked by space radiations. Anti-fuse FPGAs are preferred in space applications. Xilinx, Altera, Lattice are major champions for designing the FPGAs. In FPGAs, every component is present. It is a sea of components. Adders, multipliers, memories, tri-state switches, flip-flops, lookup tables, interconnects, and everything is programmable. When you're designing a circuit on a PCB board, once it is designed, it is fixed. And if anything wrong is detected, you cannot do anything with it. It has to be discarded or desoldered. If you have a microprocessor board, here hardware is fixed, but software you can change. If you see FPGA, here hardware is reconfigurable as well as program is reprogrammable. Both the things, hardware as well as software, they can be reprogrammed, reconfigured. Processors are power hungry devices. ASICs have zero, almost negligible power consumption. FPGAs are between processors and ASICs as far as power consumption is concerned. Time to design, FPGAs are very fast. FPGA components can take only few weeks to design a circuit where ASIC has taken 1 year. FPGA based circuits can be designed in few thousand rupees where ASIC has taken lakhs of rupees. Time to market FPGA based circuits is very small, and time to debug is also very small. You can do online debugging. If your consumer is using the FPGA based product and now you see some bug or you want to update it, you can update at your end, and then you can send updated code to that person who is sitting in different country. It can be downloaded to that FPGA. It start working in a new fashion. So that is the beauty of HDL side. ASICs are not reprogrammable. Once it is designed, you have spent millions of rupees, so many years, and once it is designed, you have to accept it. If demand is less, it is very costly. If demand is large, then cost goes down. Suppose you are asked to design a drink drop machine. It's a very common problem given in all the books. We have to design a system where cost of drink is 3 rupees and denominations options are 1 rupee and 2 rupee. Right? You can insert 1 rupee coin, 2 rupee coin, cost of drink is 3 rupees, and at the maximum you can insert only 4 rupees because cost is 3 rupees. So what is the state diagram? What is the state diagram? You have to design the circuit. You have to design a controller. Coin receiving unit, drink drop unit, coin return unit, they are available in the market. Right? Your controller will decide how smart is your drink drop machine. So what is the state diagram of that? I will just draw the state diagram. I and J are the inputs for coins. I say 0x means no coins. 10 means rupee 1. 11 means rupee 2. These are the options. When you are inserting rupee 1, I becomes 1, J becomes 0, rupee 2, it is 1, 1. 0x means no coin has been inserted. X, Y are the outputs. If you have inserted 3 rupees, X will be 1, Y will be 0. Drink is given, no coin is returned. X is 1, Y is 0. If you have inserted 4 rupees, X will be 1, Y will be 1. Drink will be given and 1 rupee coin will be returned. So This is state S0. No coin has been dropped, so it is waiting for the coin. Now you are inserting 1 rupee coin. 10 is 1 rupee coin. You are inserting 1 rupee coin, but X is 0 and Y is 0. You have to insert 3 rupees. Again, you are inserting 1 rupee coin, 1 rupee and 1 rupee. It is not 3 rupees, so X is 0, Y is 0. And then 1 more rupee is given, and it becomes 1 0. X is 1. Drop the ring, and no coin has to be returned. 1 rupee, 1 rupee, 1 rupee is 3 rupees. You are giving 1 rupee coin and then 2 rupee coin. Again, it is 3 rupees. 1 here and 2 here, so 3 rupees. Drop the drink, don't return the coin. Or 1 rupee here, and then 2 rupees here. One rupee here, and then 2 rupees here. 2 rupees, which is 1 rupee. Coin has to be returned and drop the drink. And if it is 2 rupees here, 2 rupees here, and then 2 rupees here, then this path. Or 2 rupees here and then 1 rupee here, then this path. This is a state diagram. But it requires practice. You have to understand the definition, specifications very clearly. Once the problem is understood, 50% solution is already achieved. And if a problem is not clearly understood and you are asked to design a motorcycle, you will design a cycle. So problem has to be clearly understood and follow the steps to design the things. Now HDL code for this pulsar. Do you know HDL, VHDL or Verilog? VHDL or Verilog? They are working. VHDL. Verilog is simpler. Very easy to write and very easy to understand. And if you know VHDL, you can easily understand Verilog. This is a state diagram. And this is a Verilog code for this. Initial keyword is module, then inputs are defined. In a pulsar, you have inputs S, X, clock and reset. Outputs are P and L. So simply write output P, L. And these are registered variables, P and L. Registered means they retain the value unless you override them. And each state has to be given a 2-bit code, right? So AB register state is a 2-bit code, and output is also a 2-bit code, P and L. It's a 2-bit output. State has to be a 2-bit code, and then states are defined. When you are drawing a state diagram, one more important thing is you must know how to assign codes to these state diagrams. If I have 3 states, I write here 0, 0, 0, 1, 1, 1. Or some other student 0, 0, 0, 1 and then 1, 0. What is the difference? 0, 0 code is given here, 0, 1 is given here, and here you have a choice 1, 0 or 1, 1. Which one you will prefer? 1, 1, because what is the answer? Why? Finally, what are the consequences? If you are writing 0, 0, 0, 1 and 1, 0, So in last two codes there are two transitions, and two capacitors will be charging. Whereas if you are writing 1 0 and 1 1, only one transition and only one capacitor, so you are saving energy also. So finally energy budget is reduced if you are assigning the codes using these given techniques. You should not assign the codes in any order. There will be huge power dissipation in the circuit, heating in the circuit. And there are techniques, there are research papers available how to assign codes to the state machines. So that is also a very important part. And then here we have designed the state decoder, which is deciding the next state, output decoder, and in each state we have written the outputs. See this, if you are in state S0, initial state, if S is 1, if S is true, the next state is S1. Otherwise, if S is not high, you are in the same state. If you are in state S2 and X is low, if X is, it is assumed to be low active here, or if X is active, if X is low, the next state is S3. I have said if X is high, repeated pulses must be generated. If X is low, one pulse should be generated. If X is tested to be low, don't go back to state, don't go back to S1 from S2. And if this is not true, if X is not low, means if it is high, then go back to S1. From S2 you are going back to S1. So you are repeating the generation of pulses. And when you are in state S3 and you are waiting for S to go low, if it is going low, go back to S0, otherwise continue to wait. It's very easy to write in Verilog. Can you tell which simulation tools are available for simulating VHDL or Verilog? Xilinx is there. Model Sim is there. These are two popular options available. For synthesizing, which tools? Xilinx has its own synthesizer. In Altera you have Quartus as a synthesizer tool. Altera and Xilinx are at the top for designing the tools for FPGAs and for manufacturing the FPGAs. And for this, I will show, this is a module for a adder. You can read the lines, it's very easy. It should be adder of size 8 bits, so parameter width is 8. A and B are the inputs, each of size width minus 1 means 7 down to 0. Parameter is width is 8, so 7 down to 0. 8 bit is the size of A and B, and output should also be of same size. And then simply write assign sum equal to A plus B. In Verilog, if I am writing the statements like this, assign This line says whenever A or B, or I'm writing it for full adder output, whenever A, B, C changes or any one of them changes, execute these two. These new values will be exclusively odd and the result will be given to sum. And then these values, new values, will be given to this expression and carry will be computed. If I write it like this, assign this hash represents delay. After 10 units of delay, first update these values A, B, C, and then after 10 units of delay, this computed expression result will be given to sum. That is the meaning. Update this expression with new values of A, B, C, and after 3 units of delay, send this result to carry. But this assignment has a different meaning in Verilog. If you're writing like this, take new values of ABC and compute it and assign sum to this after 10 units, and so long as this processing is going on, don't execute this. If you're writing assignment like this, equal sign, this execution will start only after 10 units of delay when it is completely executed. Now execute it and send result to this after 3 units. It has waited for 10 units here and 3 more units. So total delay here is 13 units. And here delay is 10 units. So sum and carry are not reaching at the same point of time. And if I'm writing like this, it means start updating this as well as start updating this. The right hand sides are updated simultaneously. It is updated after 10 units. It is updated after 3 units. This may be the inertial delay of this unit. This may be the inertial delay of units. Right? So this is the difference. If it is assignment is like this, right hand sides, all right hand sides are updated, and then the results are given to left hand sides depending upon individual delays. If assignment is like this, then this cannot be executed unless this is completely executed. So this delay accumulates. This is called blocking assignment. And if you are using like this, these are called non-blocking assignments. Nothing is blocked. Every execution is going on parallelly. Suppose you have given parameter delay is 100. Then you are writing always input is clock So what is this? And initially you can take there is some variable clock and it is complementing This will produce a train of square waves. Clock, it's a clock generation circuit with a on time 50 units, off time 50 units. But always block means it is a continuous generation. It never stops. It is always generated. Or if you write here repeat, you can write here always, or you can also write it as forever. Forever means continuous generation. It will stop only when entire memory of your computer has been exhausted. It will stop only. Or you can write repeat only generate 50 cycles. So these are different ways to produce clock. And then it can handle transistors also. You can model transistors, you can model them with strengths and so on. This is a controller for that computation. This is the algorithm, and this is a controller for this. We were asked to solve this controller. We were asked to design a controller for this. X is 0, Y is 0, X is 0, I is 0. So initially in state A, X is cleared, I is clear. Then when they are added, I should be I plus 1, X should be X plus 1. So X load and I load should be there. And then in state C, decision is made. If I has not reached 10, then go back. There must be 10 iterations. If I has reached 10 and X is less than 0, then cleared Y. Or if I has reached 10 and X is not less than 0, then clear X. So this is a state diagram, and then I am directly writing a Verilog code for this. Always positive edge clock, negative edge reset. Whenever clock edge goes positive, following executions will be done, or whenever reset goes down, negative edge, following executions will be done. Case there are so many states, and we use 3-bit code for this and use a case statement, 00 state, 01 state, and so on. In each state these activities are done, and finally the controller is designed. So like this. Questions from your side? Questions from other centers, please? Please ask questions.
So if there is any query from any nodal center, please ask. Okay, if you have any query, please turn on your mic and then you can ask your question.
Hello, good afternoon, sir.
Good afternoon.
IIT Madras.
Yeah, please go ahead.
Question is, the tunnel will be designed by the PhD language?
Which one? Which one?
So PhD.
Yes, you can design using VSTL or Verilog. This is your choice. If you know VSTL, you can design these circuits, controller or data path using VSTL or otherwise Verilog.
Okay, sir. Thank you.
Okay, any other query from any other center? JSS Noida, please switch on your mic if you want to ask any question, please. Your voice is not coming here. In between, if any other center has any question, then you can go ahead with that. Okay, if there is no more query, then I think we can stop this session here. And please, yes. So we are really thankful to Dr. R.K. Sharma from NIT Kurukshetra for accepting our invitation and giving us this excellent talk on first talk was on low power VLSI design, and so many concepts were really good, and so many good things were taught during that session. And after that, next session was on Verilog, and there was a very good exposure of state diagram, starting from state diagram, how you can proceed for writing your HDL code by using Verilog language. So all these sessions, I think all of you have enjoyed all these sessions. So now it is time to once again thank our expert speaker from NIT Kurukshetra. Sir, we are really thankful to you for accepting our invitation and for giving us this valuable time. And now we announce a break, lunch break. As you all know that we are already going behind schedule, so we will be back at 2:30. So you have 50 minutes time. Please enjoy your lunch, and then we will be here at 2:30. Thank you.
लंच ब्रेक दिखना चाहिए ना।
हम भी दिख देते हैं हमारा सर्वर
नहीं दिख रहा। ऊपर फोकस चेंज कर दो। पता दिख रहेगा लेकिन स्टार्ट हो गया।
Good afternoon to everyone. Now we are going to start today's third session of VLSI in analog design simulation, which will be delivered by our expert, Mr. Deep Sahgal. Mr. Deep Sahgal is working as a scientist in VLSI design in SCL, which is Semiconductor Laboratories. Um, he joined SCL in 1998 as a VLSI design engineer. During his more than 17 years of experience in design, he has worked upon many projects in various domains on 32.18 micrometer of technology. His first major work was in biomedical field for the design of ultra-low power pacemaker chip. His second major work was related to failure analysis and successful mitigation by about 50% of a problem of audio disturbance faced in landline phone. He has been
बोल देना सॉरी फॉर इंटरप्शन ड्यू टू पावर फेलियर.
ऐसे दोबारा से स्टार्ट करना पड़ेगा स्टार्टिंग से.
Hello. Hello. Hello.
Sorry for interruption due to some failure. So we are going to start our third session of VLSI in analog design simulation, which will be delivered by our expert, Mr. Deep Sahgal. Mr. Deep Sahgal is working as a scientist in VLSI design in SCL, which is Semiconductor Laboratories. During his 17 years of experience in design, he has worked upon many projects in various domains on 32.18 micrometer technology. His first major work was in biomedical field for the design of ultra-low power pacemaker chip. His second major work was related to failure analysis and successful mitigation by about 50% of a problem of audio disturbance faced in landline phone. He has been involved in project for the development of infrared camera for night vision applications. His recent works has been in the field of power management, CMOS-based imaging test chip, and design of 16-bit transceiver. Now I request to our expert to continue this session.
Hello? Hello? Hello?
Um, what we'll be seeing in this session is the analog design simulations. And if you see, analog world is a little bit different from the digital design or the digital world. So before we go into the things of simulations, let us find out how do we understand or how do we distinguish in the very fundamentals the word analog. So let me start with just this basic definition. Is it analog, or how, see, in today's world, when we talk of VLSI design, when we talk of microelectronics, and this technology took its genesis in somewhere in the 1957, and 1948 first transistor was developed, 1957 first IC was developed, and over the 50 years this technology has seen an exponential growth. No other technology in this world has sustained the 50 years of exponential growth. Even the steel industry could not come close to it. So we can think of that what impact this microelectronics particularly has created in our social infrastructure. In fact, today all the main gadgets we are having, the smartphones, the last thing which it could produce, you can see how much intelligence has been put into that gadget. So where from this all is coming? This is coming from the world of VLSI design, or what we call microelectronics, or the IC design. Now we hear of many chips. We hear of analog chips, we hear of digital chips. In our curriculums we read mixed signal chips, RF chips, memory chips. So where is the bottom line which distinguishes that which type of circuit I am dealing with? Is it analog? Is it digital circuit? Is it memory? Is it RF? Now to answer this, we have again to see how analog differs from the digital. Basically, when the industry talks of analog or digital, they are only and only concentrating upon the signals which they are to deal with. Any circuit has to process the signals, the information, and if you see this table which is in front of you, the category on the top is amplitude, time, and signal type. Now we all know when we say anything analog, we mean that on the y-axis is the amplitude, on the x-axis is the time, and both are continuous as far as our measuring system, as far as our detectability goes. We do not see any jump into the things. We do not see any quantization into the things. So it is all continuous on the y-axis, which is the amplitude axis. It is all continuous on the x-axis, which is the time axis. And then I categorize that signal as analog signal. Now, what if I make the time axis discrete? So that is called sampling, and it can be uniform, it can be non-uniform. Again, what if I make the y-axis, which is the amplitude axis, quantized or the discrete? Then the first step of sampling and the second step of quantization is making me to enter into the digital world. And therefore this A to D block, analog to digital converter block, is a very, very important block as far as we as a designer goes. But there is a third category. If you see the last row of this table, what it is saying is that time is being discretized. Time has been discretized. So somebody has done the sampling, but somebody has not done the quantization in y-axis. He is still keeping that axis, he or she, as continuous. Now, what is this type of signals? Do you call it analog or do you call it digital? See, this is a special category of signals, but as far as our basic analog digital differentiation goes, it is analog in nature. So this word analog comes from y-axis, or the amplitude axis of the signal is not being discretized, whereas time axis is. But still the signal retains its properties of analog. Analog basically comes from the word analogous. The main essence which you have to carry with you all over your career is, if you are into the analog world, you have to represent the information as it is, although you are processing it. But this analogous thing, this information in the same similar way processed, should not be forgotten. So this gave birth to switched capacitor circuits, this third and the last row. And these are very important category of circuits as far as analog design goes. And how to simulate those circuits is again a very tough thing, because they are sampled in the time domain, they are not sampled in y-axis domain, that is amplitude domain. Now this goes into the analog and digital. Now what is design and what is analysis? Just the basics. When I say the word analysis, see, I have a circuit and I have to derive out its properties, its specifications, its parameters. That is my goal, and that is the goal of almost all the books. The last problems which we were dealing with in our BTech and in our other school education, we were always oriented towards the analytical work or the analysis work. But when I do the design, I have to go from the specifications, properties given to me, to realization of circuits. So design is the backward tracing from solution which I must attain to how I can attain. So design is a difficult task, because one property set given to you can convert into many circuits. For example, let us say I have to make a 10 ohm resistor. I have to make 10 ohm resistor. I can do it with the 5 ohm in series, 20 ohm in parallel. So there are many solutions of the same desired set of properties, and herein lies the creativity of the designer. How creative he can be, there is no limit into it. If you see the innovations, there is no limit. So now coming to our main important subject, how integrated analog design differs from discrete analog design. You all were doing, and we all were doing this in the college life, when we were doing the discrete analog design. But now today we are seeing integrated circuits, and it is little different from discrete world. How? See the first point, the substrate is same. Substrate is same where? In discrete or in integrated? It is same in the integrated design. See, I am realizing everything on the same substrate. I am realizing everything on the common substrate. And this commonality of the substrate wherein all the devices are realized is very different from what the discrete world looks like. Discrete world means I have a PCB, and I am populating it with various components. But these components per se have been realized in the different substrates. So is it advantageous to me or is it disadvantageous to me is the question. If I can realize all the components, all the devices on the same substrate, I have a very important degree of freedom which I have attained, and this is not there in the breadboarding or PCB. The degree of freedom I have achieved is, if my two components are very close by, imagine, then their properties are very similar. So matching of the two components is only and only possible when I realize them with the same manufacturing conditions, with the same processing on the same substrate. So two transistors kept side by side are very similar in their properties, and this matching principle has been nicely exploited in the integrated circuit, particularly analog designs. Discrete world, you put two transistors, their properties, their characteristics will differ. So I gain 1 degree of freedom when I say substrate is same or substrate is common in the integrated world. But there is a disadvantage also, and that disadvantage, how to convert it into simulations, is another chapter. But the disadvantage is that one component can interfere with another because substrates are common. So in the IC, when the million of transistors are there, the substrate interference is the topic of a very high research area, and how to mitigate the problems of substrate interference. Now coming to geometry of active and passive devices, what I mean here is that see, if I have a components in the integrated circuit, then I have a control over their geometries. And in our 180 nanometer process of semiconductor laboratory, we can have the lengths of the transistor varying from 180 nanometer, that is 0.18 micrometer, to around 20 micrometers, and widths can vary from around 220 or the 0.22 micrometer to around 100, or in the multiples, if I say, it can be even 10,000 micrometer. So this type of flexibility, not only in the active devices but also in the passive devices, where I can have a resistors with the W and L, width and length, varying right from, let us say, 2 micron to maybe even to the 100 microns, is very much possible when you enter into integrated circuit world. Now these all things you have to remember, because one day when I enter into the simulations, I have to put these values somewhere. So first of all, I should know how much is my capability when I am doing IC design. It is different from discrete world, and simulations are the cornerstone, or the simulations are the keywords which is there. Unless and until you simulate, you cannot pass the chip into fabrication. And we have there is a limitation also in the IC design. You don't have many components available to you. For example, if you want to populate a PCB, you can have inductor, transformer, capacitor, resistor, even power MOSFETs, all at your wish. But in the IC world, when you enter into the standard CMOS process, you find that your choices of devices is limited, but your geometry control is marvelous. So there is a trade-off involved. Let us see how this analog design flow originates. Now we all know every design starts with the functionality and specifications. Now first I have to be very clear of its functionality. I have to be very clear of specifications. When I say I have to be very clear of, it's not easy. For example, take the operational amplifier, a very workhorse of the analog design world. If you see an operational amplifier specifications, there are around 17 specifications we have to deal with. And I'm not having the list right now, but you can start with the open loop gain, you can start with phase margin, gain margin, slew rate, settling time, CMRR, PSRR, offsets, and then output impedances, and then input impedances. And you have to think of everything when you are designing an operational amplifier, and certain key things which are required in your applications. So this specification part is a lengthy part, and you have to cleanly understand how this specification will be simulated, how this specification will be tested, and what do I mean when I say open loop gain, and what do I mean when I say phase margin, these type of things. But once you are very clear of this functionality, this specification, enter into the design process. What is the first step of design process? Bring your paperwork into computer. Till now, analog design still goes with the paper and pencil type of approach, but one day you have to enter into the computer world, and the entry point can be many types of software. For example, in the Cadence there is a Virtuoso schematic editor, and in the Synopsys house there is a custom sim. So through the Virtuoso schematic editor you enter your design into the schematic form in the virtual environment. Or you can also write a netlist, you can also write few commands, and your all design is represented in the text form in the virtual world. Now comes the simulations. Now you have to simulate your design. What is simulation? Basically you are doing the analysis of your design with the help of computer or some software. And once the simulations are clear, you are very much convinced that okay, your specifications are being met, proceed to physical implementation or the layout. Once the layout, and what is that verification, physical implementation and verification, the fourth block. Verification is basically the design rule checks, DRC, that your design meets with the requirements of fabrication house, foundry, and also your physical implementation matches with your schematic, because now you have converted your design into few sets of rectangles. Now these rectangles really matches with your intention, with your schematic. You have to be careful of. And then once this is also clear, proceed to parasitic extraction. What is this parasitic extraction? Nothing is ideal in the real world, and no wire is ideal. Never think of wire as the resistor only. Wire has capacitance also. At the high frequencies, wire has a skin effect also. So take all these considerations into account, and there is a parasitic elements everywhere in your design which are not visible, and they can very well kill your performance also, the specifications which you achieved on the third block. So parasitic extraction I have to be careful of. I have to extract all the unintentional elements in my design in the form of resistors, capacitors, mainly not inductors. Inductors come at very high frequency. So mutual capacitance, self capacitance, and the resistors. These are the three main elements extracted after the layout, and they are attached with your original netlist or your original schematics. And now again a time you see the loop going from parasitic extraction to simulation, that blue color loop. You have again to enter into the simulations once more, and now if here also you meet the specifications, proceed to the fabrication. So this cycle is a cycle of analog design flow, and it's not every step is a quite a deep and involved step. And if you see the golden arrows in the analog design flow, you see that there is many loops, which I am not actually, I am talking of as if everything is proceeding very smoothly from top to bottom, but never things proceed that smoothly. You have to go into the loops. If your after parasitic extraction your specifications through simulations are not meeting, you have to change somewhere. Where to change? Either in the layout, okay, that is easy, but sometimes the change can straight go to the second block, your design itself, and then your whole cycle is repeated. So your time schedules will not be met, and therefore when you start your design, think of the end lines. In the end you will face parasitics, so consider them right in the very beginning of your design. It's a good simulation practice to incorporate all your parasitics into the simulations right at the beginning of your design. Just give some R, some milliohms, some ohms there will be. So give that and then see the performance of your, let us say, operational amplifier. What do you gain really from the computer simulation techniques? See, first thing is definitely I have eliminated the need of the breadboards. Okay, that is fine. I am now all into the computer. Breadboard task is over. But there is another very important thing which is related to simulations, and you should explore this. You should use this to your highest capability. Monitor signal at any point you desire. This is not possible in the breadboard or in the PCBs. But here, because you have the access to every node of the circuit, every branch of the circuit, so you exploit this and use it to your favor. So in the simulation, remember some good practices. One is where to monitor the signals, and second is bring that parasitic effects right in the beginning into your design. It will save you much time. And also very easy to modify the circuit. Yeah, because it is only the text you are writing or some schematic you are drawing through the computer softwares. And there is two very important areas. One is the temperature effects on your circuit, and other is the process effects on your circuit. No circuit is immune to the temperature variations or process variations. One day you will realize that, okay, my design works very well at 27 degrees centigrade. But what if my design goes to minus 40 degree, minus 55 degrees centigrade, or to extremes of plus 125 degrees centigrade? I am basically talking of military range or the industrial range. So you have to think of, and why only to think? You can simulate. Just by one command you can change the temperature of the entire simulation environment, and again simulate your circuit at minus 40 or 125, and you will find many dramatic effects of the temperature. Sometimes this is another area where you have to struggle with. For example, in the band gap reference. Band gap reference is a block which is supposed to maintain the constant voltage over the temperature. Can it? No, there is a limit. Some 10 ppm, 40 ppm per degree centigrade type of figures comes. So these are the two important areas. What is this ability to easily analyze circuit at various processes? Say in the manufacturing, always consider that the file which you are using for simulations, I will come to that, they are only typical files, but there are another files which are given by the foundry and which are over the various extremes of the process. For example, let us talk of one single element, threshold voltage of the MOS. We all know in 180 nanometer process type, these threshold voltages are somewhere in the range of 0.4 to 0.6 volts. Let us take 0.5 volts. Now in the 0.5 volt is only typical, that too at 27 degrees centigrade. What if the extreme comes for the manufacturing? This 0.5 volt can become 0.4 volt, and it can also become 0.6 volt. So this is the range of the process, and with temperature there can be minus 2 millivolt per degree centigrade of change. So for 100 degrees centigrade change, there will be 200 millivolts, or 0.2 volt again change. So considering this change, even your simple Vt of the MOS is not constant, but it is varying, and you have to take this also into account through simulators. What is now, given this all dimensions, given this all beautiful world of simulators where many things are very easy to do, you will feel that a simulator is as if everything for your design work. But again, that is also not so. See, I am highlighting certain weaknesses in the computer simulation techniques. The first and the very great weakness is the accuracy of the models. What do I mean when I say accuracy of models? Basically, if okay, we can come to this thing and we will cover that in detail in the next few slides. But remember just one paradigm. Your simulation is as accurate as your model. That's all. That is the bottom line. If your model is very weak, if your model is only plus minus 20% accurate, never expect your simulator to give more accurate answers. So your dependency is on the model first. Then sometimes big circuits, you do not know how they have converged. If the circuit is of 300 transistors, the convergence may become issue. Now in the nowadays simulator, this has been very much taken away by their advanced algorithms, but still be aware there can come the convergence issue in the simulator, and you have to tackle it by workaround solutions. Then time required for simulations. This is a very important area. See, time required for simulation, what do I mean by that is, in the breadboards or in the PCBs, whenever you populate it, you put it on the CRO and some vectors, and you start seeing the results on the CRO. This is not so in the simulations. What happens? You put your circuit in the simulator, you fire the command, and now if it is a very big circuit, let us say of 10,000 transistors, it will take maybe many hours to get first result. And again, if you have to change something based on your output of the simulator, it will again take that many hours. So the simulator world is slow world still as compared to real world. It all depends upon how many servers you are putting. Are you putting distributed processing? Are you putting compute farms? All that in your basic setups, which industry does, but still there is a high time associated with big simulators or the big simulations. And never use your computer as a substitute for your analytical work which you have to actually do. This is big weakness. Even I have fallen into it, that I start blindly taking the numbers which are coming out from the simulator as if they are everything, and stop thinking, okay, op-amp gain is coming 80 dB, fine, 80 dB, 80 dB. Someday you see that somewhere you have done a blunder in your file. So simulator was giving you right number, but only what it was seeing. So it was a wrong input, wrong output was coming. You have to be very careful of when you do particularly analog simulations, because their analog problems are multi-dimensional problems. It's not only time and only output of bits. No, it's a much complex than that. So you have to be careful of your analytical. Never drop your analytical approach just because you are having a powerful computers and simulators. So now what is this industry EDA vendors are offering? The SPICE, you must all have heard of the word SPICE. It is the acronym of the simulation program with integrated circuit emphasis. Now SPICE has been I should say the research of the Berkeley University over more than 10 years, 10 to 15 years. So they put this research, and then came this SPICE engine. Their only aim was to really make a very good analysis, very accurate analysis of the circuits. So later on, what happened? This SPICE was procured by many people. So sometimes it went to one industry, then that industry was overtaken by other industry, and over the years there are many flavors of SPICE has come in the VLSI design world. For example, T SPICE, P SPICE, H SPICE, and even some big houses are having their own SPICE. For example, Intel, they will be having their own SPICE, which is not available to you and me as outsiders. So we use generic simulators which are available to all the people, and there are three basic houses, EDA vendors, big vendors. One is the Synopsys, Mentor Graphics, and Cadence. Only three big people have remained in the EDA industry world as of now. Many small companies have been overtaken, or they have been merged into these big companies. Now what they are offering, Synopsys is offering HSpice, again HSpice RF, and again XA, which is FastSpice. What is this FastSpice? HSpice, when I say, it is basically a generic and a common simulator which is used, and one version may come somewhere around 3 to 4 lakhs. But when it comes to XA, or the HSIM was another name, FastSpice. See, the problem is this. If I go back, in this flow only there is a problem. If you come to the second last block, parasitic extraction, already you were making a very big circuit. Let us say you were making some mobile chip for analog, and already it was containing thousands of transistors. And when I came to parasitic extraction, I extracted resistors, I extracted capacitors, and these elements can again go to even 1 lakh. 1 lakh resistors, 1 lakh capacitors. Last circuit which we were simulating in our floor was somewhere it was carrying 1,75,000 active devices, which is NMOS and PMOS, and 1 lakh resistors, 1 lakh capacitors. Because we are extracting the resistors, capacitors up to the level of few milliohms. We want it to be very accurate, but you are paying the price for accuracy, the time, and the complexity. Now this big circuit, if I put in the basic HSpice, it will take me 1 month to receive the first output. So industry already knows we are making this chip, and they are making even the very high advanced generation chips. So how to deal with these multi-million transistors and passive and active devices problem? They turned out with the FastSpice simulators, which are very much used nowadays, and they are very costly. And this FastSpice is basically it is the corrections, not corrections, it is the modifications done in the algorithms, internal algorithms of the simulators, which is basic HSpice, to make it fast. But remember, when you make anything fast, you may be losing accuracy. There is always a trade-off, as if, between the speed and between how much accurate you can be. So they have traded off with the accuracy to make your simulations fast. So FastSpice can give you the accuracy with respect to HSpice, let us say by plus minus 3% or plus minus 2% within the HSpice results. If that is acceptable to you, you can proceed. So at least, but what is the, then you may ask, if the accuracy is not good, what is the advantage of FastSpice? The advantage is that at least I know I have simulated my entire circuit with parasitic extractions, and at least I know that yes, it is producing the desired outputs, and it can be proceeded to fabrication, because fabrication is an extremely costly business. The 180 nanometer, at 180 nanometer node, there are 25 masks which are used, and one mask set around cost 1 lakh. So 25 lakh straight goes, and then comes the this fabrication, all the raw materials and everything. So it's the design community works very carefully when it starts coming to the release of design to GDS2, what you call to the fabrication. And we have to be very careful. So let me simulate complete, let me simulate over -40, let me simulate over 125, let me simulate over all the processes, let me simulate over all the voltages. For example, 3.3 volt circuit. Question is, have you simulated with plus minus 10% change, or are you only dwelling upon 3.3 volt? Wrong. You have to see of 3 volt, 3.6 volt. So these many corners you have to simulate a big circuit. You need some very fast simulators. So FastSpice is one, but Synopsys is not the only house. The mentor graphics I will not put, although it is second in my table, but the third, Cadence, is a very powerful house. And I will suggest that okay, Cadence Synopsys go very much parallel in the competitive world. So Spectre is very powerful simulator they are having, and their FastSpice is called XPS. So it can also, even the FastSpice can simulate the digital circuits. So this is the what the industry stands with respect to softwares. And HSpice RF is only meant for the RF work, which is again in the gigahertz frequency range. Now I have one question. Then you may ask how multi-billion transistor digital circuits are simulated. This is tough to see. They are not simulated in HSpice. No digital circuit is simulated in HSpice. So they have taken use of the basic properties of digital signal, which we saw in the first slide. Digital means discrete in amplitude, discrete in time. So why not to see the simulations only at the samples? Why to see the simulations over all the time? One. Why to see the simulations over all the range of amplitude? I am only interested in 0 and 1. So let me see only whether high signal is coming or low signal is coming. And that makes the digital simulators powerful. They have exploited the digital signal properties to make a simulator which is event driven, what they call, and they use that approach for the digital world simulations. Otherwise it's not possible. Digital is even billions of transistors. So they don't use HSpice, but sometimes they use FastSpice. Yes, they use. This is what you call the simulation environment. Now, if you see this figure, in the center is the simulator. And what goes into the simulator, what comes out of the simulator. The 4 or the 5 important thing goes into the simulator. First is, I will start from the netlist, which is written there. This is the technical word for your input file. Netlist is basically a text-based list of your, which is describing your circuit. It is not VHDL. It is parallel to RTL or VHDL or Verilog file, you can say, if you are working in digital. But it is something like that, written in the SPICE format, written in the Spectre format, and given to the simulator, which can be SPICE, which can be Spectre, can be FastSpice also. Then netlist itself is not sufficient. You have to tell stimulus. What is a stimulus? Stimulus is what test vectors I want to force upon this circuit. What forces, signals I want to put upon this circuit so as to simulate it. For example, operational amplifier. You want to see the settling time of transitional operational amplifier, but first you have to give a square wave to its input and then see output. So stimulus describes all your test vectors, all your environment of the forces which you will be applying upon your input or the netlist file. Then a very important area of models. Every simulator calls some model. What is model? Think of how simulator works. Ultimately, it is understanding that this is MOS, this is resistor, this is capacitor. How it is understanding how this MOS block will work through the models which is supplied to it by the fabrication house. These are also a form of text files, but standardized text files. And these models describe that what type of behavior this MOS component will give. IV curves, their QV curves, their QV curves gives the capacitances, and IV curves and their small signal curves and their frequency properties. So these all coded in these model files. See, the model industry is a big industry. Simulation industry is basically software industry, but model industry is a mathematical industry which is always on the search of a good model. What is a good model? Which can simulate or which can tell me all the characteristics of my transistors, my resistors in the shortest amount of time when it is given to simulator. It should be very ideal. So there are levels. You may be hearing of the levels which is called level 1 SPICE models, level 2 SPICE models, level 3 SPICE models, and even up to level 50. So what we are using here is level 49 SPICE models. These models really take all things into account. You know that in MOS transistor there is short channel effects, there are long channel effects. Everything is taken into account. Although it is not perfect models, there are certain weaknesses also in the BSIM 3v3 or level 49 models, but still they have come from the research again from the Berkeley University BSIM. So these models are very standard industry models which are used. BSIM is the keyword, and BSIM level 6 is now what is currently going on. BSIM level BSIM 3v3 is what we are using at present. BSIM 4 came, then came BSIM 6. 5 was, I think, not very much popular. So because they are nowadays going to 22 nanometer geometries. Now these MOSes are having very specific effects which were not there in the earlier big MOSes. So now they have to again face a new difficulties. So how to model these effects? If you can't model these effects, simulator will not tell you. Simulator only can tell you if you tell that MOS is having this effect. So model industry is a big industry, and now even the Spectre and HSPICE, they all use same model platforms. Some Philips models are also there, and some EKV model is also there. EKV is basically on the name of three scientists. It was Kramanesher, Vitos, and Enz. E for Enz, K for Kramanesher, and Vitos. So they were European models. They are not very popular in the American industry. BSIM is the keyword which is majorly used. Okay, yeah. And you see this there are other things also. Operating condition is basically it tells me about what to say, the temperature profile or the temperature sweeps which I want to carry out, and the voltages and the process. So the industry calls it PVT, process voltage temperature corners. Now comes the options, the bottom side. This option is basically what configures your, you see every software comes with some options, and even the Internet Explorer, these all softwares comes with the we do the advanced settings. So sometimes industry gives you that package in the form of some settings, but sometimes you have to tune your settings according to your requirement. I give you an example where you really require to tune your settings of the simulator, and this is one area you always remember. Never take the EDA vendor option setting as final for your simulation purpose. If you are dealing with, let us say, low power world, then that means you are dealing with the nanoamps of currents. And if you are making anything in the subthreshold region, in the nanoamp region, you cannot do with the generic setting of the simulator. Generic setting of the simulator says that even if 1 microamp is the accuracy level for the generic setting. So it means simulator goes on till it finds that okay, error between last step and next step is 1 microamps. Okay, I can stop my simulation. Simulator works like this. It keeps on simulating your circuit till it finds that error between the previous step and the next step is within your tolerance range. Tolerance range given by you or by default setting, which is in the range of microamps. So what's the use of simulating nanoamp circuit with the tolerances of microamps? It is here you have to change your simulation settings. There can be another area. For example, if I am making a 20-bit or 18-bit ADC, now if 1 volt is my total range and if 10-bit is the ADC, then LSB comes 1 millivolt. But if 14-bit or 16-bit is the ADC, LSB goes into microvolts, few microvolts. Now if my accuracy setting for the voltage is, let us say, 100 microvolts, I am unnecessarily making 16-bit ADC in this simulation setting. You cannot make. The simulator is not showing you the correct picture. Therefore, I said never throw away your analytical thing just because you are having a powerful simulator or computer. You have to very well think 16-bit ADC means microvolt of dealing I have to make. Can my simulator really shows microvolt of volt? It can, but you have to change your setting. Then it will take more time for simulation, but they will be accurate simulations. And we all have suffered this thing while doing the work, because sometimes EDA vendors also, in your training sessions, I will say, make your training sessions very powerful when you purchase the EDA tool. Ask them to again and again give you training till there should be a clean training session defined right at the purchase thing. And it is very important, they have to highlight the practical things. Yeah, and there is one more thing, which is a small thing, waveform displayer. See, simulator can give you numbers. Okay, fine, gain is this, phase margin is this, it has a capability, it can give you. But that is not enough. You want to see the waveforms. That is also important, because once this error, I was entering into this error. I was blindly relying upon the numbers, but numbers are not enough. You have to see the waveforms. Are they matches with the number? So waveform displayer is also very important. Okay, what types of analysis? Your simulator can, any generic simulator, whether HSpice, whether Spectre, whether Eldo. Mentor Graphics I didn't touch, but Eldo is their prime simulator. It has to give you operating point analysis, transient. What is this operating point analysis? This is important. See, when I design a circuit, you think we all were reading about the bias points, about the quiescent points of the circuit. Now is the time when I am putting the circuit in the simulator. Can it tell me what is the bias points or quiescent points of my circuit? It can, through this operating point analysis. .op you have to write in your HSpice. It will give you, if you put .op voltage, it will give you only voltage Q points. .op current, only current Q points. .op all, everything it will give you. So first dwell upon this answer for a time. See how much this operating point is really what you are thinking of in your analysis, paper pencil analysis, and then correlate it. Should I proceed further? Okay, fine. Transient domain analysis. What is this transient? Now I will put a waveform input, square wave. Let us say I give to some circuit amplifier. How it amplifies my square wave? This is your prime query. So now you can put through .tran. That is the keyword for the transient analysis. What is this? Okay, DC I will come. Frequency domain, very important again. Why? Because filters you have to make, amplifiers you have to make. What are these amplifier important curves? In the last I will show you some curves where few are on the frequency domain, few are also on the time domain. The thing to remember is, in your simulations you are doing two types of worlds. One is time domain simulations, other is frequency domain simulations, which are called AC simulations in your HSpice world. So .ac is the command. Command is very easy to give. .ac 1 meg to 10 meg in the steps of, let us say, 100k. Okay, you can write it, but the inner thing is, there is a chance of error in the AC analysis, in the frequency domain analysis. What happens is this: when you put a command to simulator .ac 1 meg to 10 meg, so what simulator does? It immediately converts your whole circuit into small signal circuit. You know small signal circuit, which is basically all DC gone and all current sources open, and now small signal models of your transistors, diodes, everything put into the picture. Now it runs it with respect to frequency. At 1 meg what will happen? At 1.1, because you have given step of 100k, so 1.1, 1.2, 1.3, it will keep on simulating till 100 meg or whatever you have given, last limit. But there is a chance. Why I said there is a chance of error? Because this is not the real world. In the real world, what happens? Now imagine in your circuit a transient comes. Let us say you give a square wave, let us say from 1 volt to 2 volt. Your circuit is seeing transition from 1 volt to 2 volt, and everywhere the small signal properties are dependent upon the DC signals, the input levels which you are feeding to your circuit. 1 volt to 2 volt means your DC level is continuously changing for this circuit. So your small signal is also continuously changing for your circuit. But when you did this AC analysis, you only did with one simple .op operating point analysis, and this may not correlate with the time domain. So just to say you what effect can come. Sensitivity very important. What if this resistor changes? What if this capacitor changes? You can easily do in the simulation world. So it can see the realize the power of simulator, but wisely. The power of simulator is it is offloading you with many mundane tasks which you have actually to do on the paper and pencil, but only keep on checking that it is doing it rightly. With some range of answers you should have. Noise analysis, powerful thing it can do. Dot noise is the keyword which is used in the simulators. Dot pz is for pole 0, and S parameter, of course, it is for the RF world. So many analysis it can give, almost all which you require for your design. What is the element support? These are all the elements which can be supported almost by all good simulators, Cadence or Synopsys or Mentor Graphics, anything. So you see in the end there comes the transformers, transmission lines, the voltage and current independent sources, voltage and current controlled sources, which is VCVS, CCVS, CCCS or VCVS type of things. These also are there in the simulators. How to make use of it? I will only tell you one thing. Whenever you have a big software is in front of you, devote the time in the training, as I was telling, but also devote the time in the self-reading of the manual. Highly important it is to really realize its power and just see how many commands it can carry out and what are that useful set of commands you can use right now. Make a list of it, analyze it, have a conversation with the application engineer of EDA industry. See, every EDA industry is having that software support team. You can easily write your query and answer will come within an hour. So it's a powerful technique of using those guys who are expert in their fields and understanding the simulators. Big companies, of course, these ST and Freescale type of companies, they do not wait for their engineers to understand the problem. The moment they land with the problem in simulator, they call their software engineer from the EDA industry. He has to sit there, solve their problem, proceed forward. So many times designers are unaware of what is happening back the scene of the simulators. But if you have really to work out with the powerful way, you have to understand simulator also. Advanced features, these are very important features. Okay, let me start with the Monte Carlo. What is this Monte Carlo analysis? Is this: you have a circuit of, let us say, 20 transistors. Now in the beginning we said that in the integrated circuit world there is a matching between the transistors because they are in the close proximity, they are on the same substrate. But no matching is perfect. There inside this big matching there is also still some mismatching. They are between two very neighbor transistors hardly separated by 10 micrometers. But they are not identical. So how to know the effect of this unequalness between them, this mismatch between them? And in this way there is whole set of transistors, 20 transistors, and so what Monte Carlo does, it throws away the simulation in this way that it varies all your transistors randomly. Some VT 0.5, some VT 0.45, some VT 0.65, and it will keep on simulating for one set of VTs, for second set of VTs, third set of VTs. You give command and it will keep on simulating. Even your 1000 simulations can be carried out with different sets of VTs, the threshold voltages. Now you have a big picture. Now you have a picture where it is telling you what if this set of transistors vary in this way, vary in this way, and the graphs can come on your waveform displayer. And it all depends upon you now how to interpret these graphs. Or for example, offset. Where from the offset comes in the op-amps? Offset only comes because there is a mismatch between the input transistors of differential pair. But how much offset can come if there is, let us say, 1% mismatch in the threshold voltage of the transistors? If you want to know it, throw it in the simulator. It will tell you 2 millivolt or 3 millivolt of offset will come. This is something advanced features, but again, mind it, model file should also support it. Model files are to be written in the way they are understood by the Monte Carlo analysis. So Monte Carlo per se cannot do if model files is not giving you the sigma of Vt. So they have to give sigma of Vt, sigma of many other important parameters of the MOS, also like mobility. What is this optimization? Another very powerful set of feature in the simulators. Optimization is basically this. You have a transistor from the foundry. Transistor is behaving some IV curve it is giving. Okay, fine. But now you as a model maker has to find out a set of parameters of the transistors which emulate this same behavior. So your goal is find out the parameters of the MOS transistors, a file, model file you make and give to designer, and when it simulates that model file, the curve should be very much same which they found in the testing. So you have to match the two curves, one in the testing and one in the virtual environment. So optimization is that scheme which can straight drive you to, let us say if you say RMS error over this curve should be plus minus 1%. So it will start optimizing your parameters one by one, again inside using Monte Carlo. And it will come out with the nice scheme of parameters. This set of parameters is meeting your RMS goal. And if your goal is unrealistic, it will come out with no solution. But in this way, you can match a real world curve with the virtual world curve through the schemes of optimization of the simulator, this feature of the simulator. Parametric sweep. Parametric sweep is something, let us say I have a temperature which is given by .temp command, .temp command of the simulator. .temp 27, if I write, simulator understands it that I have to simulate it at 27 degrees centigrade. So all model parameters made according to 27. But what if I have to .temp minus 40? So again it changes the Vt of the MOS and everything and again simulates. But what if I have to make a sweep of the temperature from minus 40, minus 35, minus 25 to the 100, 110, 15 like that. So I will just write .temp and let us say one variable which we do in the C language, let us say variable is x, and I will parameterize this variable through the command of .param x equal to minus 42 some 125, like that I can use. So basically I am sweeping the entire temperature from minus 40 to 1 .param x, and in the .dc I will write .dc x, sweep the x from minus 40 to 125 in the steps of 1 degree centigrade. So many curves will come, and now you are seeing the response of your circuit with every temperature. So it is a sweep. Sweep can be used for anything, for resistor, for MOS, anything. And data driven analysis. Okay, I have capacitor, I have resistor. I will make a table. Resistor goes 10k, capacitor goes 10 puff. Resistor goes 100k, capacitor goes 1 micro. Let me have few data points. I can cover it in a table. Throw the table to dot data analysis, and it will be data driven analysis. It will simulate for all the entries, every row of your table, and will give you the output. So these are the way we use, like for example, how we can do data driven analysis into our use. In the beginning I said we need PVT corner analysis, process, voltage and temperature. Forget process, voltage and temperature can nicely be covered in dot data driven analysis. What it will do, voltage I make one column, temperature one column, voltage 3.3, 3.0, 3.6, temperature minus 40, 27, 125. It will do me for these corners, every row. So you keep on increasing your row, you keep on increasing your cases, it will keep on simulating. So it will, in the end, the picture will be, okay, the output varies from this to this over these corners. So it is called a box analysis or the worst case analysis. Monte Carlo is more realistic analysis. Not only that, every software simulator comes with the output processing features. What it does is basically you give an output to the simulator. Simulator gives you some output, and you are not limited to it. You can further process this output, and you can make much use of this output. It has given you only numbers, but you can make use of these numbers through these algebraic functions, algebraic operators like division, multiplication, some sign functions, log functions, and some automated measurement functions. Simulator has this capability, find when, what when type of analysis it can do. So it can, suppose you give it, find the gain at 100 meg. If you write it like this, it will tell you a number. Gain at 100 meg is, let us say, 20 dB. So they can give this type of outputs. But having said all this, there is a danger, and I have almost touched upon that danger, but let me again revise it. It is just a numerical calculator. Never throw away your analysis just because of simulator. Simulator is a number cruncher system, and these numbers can all be wrong if your setup environment is wrong. If you have given the wrong vectors, wrong answers you are seeing. If you have given the wrong, let us say, netlist, some error you have done. Once what can be done is, for example, two nodes names are same. Let us say one MOS is having the node name of drain is at D, gate is at G, source is at S, body is at B. This is the way you describe the MOS. By chance you made the second MOS also drain at D, gate you G1, S1, B1, but D is not D1. So unintentionally you shorted these two drains. You gave it the number, and now simulator is taking it as if the drains are shorted, and you are getting the wrong numbers only. So never rely, see your file very carefully, see your stimulus also very carefully, your operating conditions also very carefully, and again accuracy depends upon modeling. If model is not accurate, IV curve doesn't matches with the real world and virtual world, forget about simulators, they cannot help you. So and also, yeah, read the manual to familiarize yourself with, as I said in the beginning. Just see this curve. This is what you can expect from simulators. Now this curve, x-axis is the frequency domain. It is basically a frequency domain power supply rejection analysis. It is of one circuit which is voltage regulator. So power supply rejection means if there is a fluctuation happening in the supply, how much it rejects, because voltage regulator has to maintain a constant output voltage. What this curve tells me, it is that frequency domain x-axis goes from 1 Hertz to 100 megahertz, one thing, and the y-axis goes from some 10 dB to 70 dB type of thing. And if you see, after 1K it is falling at again that 20 dB per decade rate, again rising somewhere at 1. This type of curve analysis simulator is very powerful of doing. If you do it through hand analysis, very tough for you to go for 1 meg, 10 meg type of frequencies. What will happen? You have to see, so many transistors are there. It almost becomes impossible to do hand analysis. Hand analysis is only good when we read some basic analog design book like Alan Holberg, first few chapters, where it is given common source like those circuits. Okay, one transistor circuit you can do much, 2 transistors still, but when it comes to big regulator type of circuits, 100 transistors, I have to simulate. And see, this is the time domain curve. In here, basically it is the load switching. If you see the first curve, it is the load coming from some level to some level. Let us say some high milliamps to low milliamps. Now the second curve is the current output of the regulator, and third curve is the output of the regulator, voltage output. So current is fluctuating and voltage is quickly settling, and then current also settles to some level. So what we are interested with, that how much time it will take me this current to settle. So these type of things you can do through waveform. This is the output of simulator thrown in the waveform displayer, which is custom wave view from the Synopsys. So custom wave view, if you see, and upper ye sare on the upper screen, if you see, there are the many commands and some are cut also. Those can be used for the processing. Like that it goes to yeah, again a power supply. Sorry. Yeah, it is again a line switching type of curve, and there is a load regulation and short circuit protection. This curve is basically if I short circuit the regulator output, what current it will come to? It can burn also, but it is showing me no, it will not. If you see the second curve, the x-axis is the resistor. So resistor going from 50, 40, 30, 20, 10, 0. And the current, which is y-axis on the second curve, settling to somewhere 350 milliamps. So that is the limit it is coming to. And these are the analysis which is, see, if you categorize them, they are frequency domain, they are transient. Only two types of analysis we are doing in the simulators. Yeah, thank you. Now if I can also show something right there, and some spice formats I can write there, but if the need be, because we can read the manual and always find out. Yeah, it is not
You can ask for queries.
Yes,
please. So now house is open for queries. If you have any query, then you can ask your queries. Nodal centers first. If any nodal center has any query, then please go ahead.
Hello, sir.
Yes. Please go ahead.
I am calling from JSS College, Noida.
Okay. Yeah, what is your query?
What will be the ideal sigma value? Sigma value, is it depends upon the complexity of circuit?
Can you repeat your question?
For Monte Carlo simulation, what will be the ideal value of sigma? And second part is it sigma is depends upon complexity of circuit?
Okay. Yeah, your first question is that what will be the sigma value of the circuit, and does it depends upon the complexity of the circuit? In the Monte Carlo analysis, the sigma value comes from the fabrication house, in the sense that just think who is the supplier of the model files. Model files designer is not making, even EDA vendor simulation is not making, only the fabrication house is giving me sigma. For example, the sigma of a threshold voltage of MOS can be somewhere in the range of maybe around 30 millivolts, plus minus 30. So what Monte Carlo does, it takes this sigma and it spreads. For example, in one simulation, it will use exactly nominal value, 0.5 volts. In next simulation, it will use 0.5 plus 2 sigma. In other one, 0.5 plus 3 sigma. If I have specified the Monte Carlo command with 3 sigma, then it will go to 3 sigma. If with the 5 sigma, it will go to 5 sigma. And basic thing is that sigma has come from the fabrication house on their fabrication foundry, how much it varies. But I can make use of till 3 sigma, which is normally the case, and it will simulate till 90 millivolts plus minus over nominal.
Any other query?
Hello. Hello.
One query.
Yeah, please.
Yeah,
Hello.
yeah, please. Sorry. Can you repeat your question?
Okay.
Just.
Okay. I think ABS Ghaziabad, please wait. One query is there from JSS Noida. Please go ahead with your query.
One query is what is the importance of parametric sweep in the designing?
What is importance?
What is the importance of
Parametric sweep.
Parametric sweep. Okay.
Parametric sweep? Okay.
See, in the parametric sweep case, one example I gave you, it was related to the temperature. Let us imagine I have made a circuit at 27 degrees centigrade, and now I want to simulate this circuit from -40 to 150. How will I do it? Either I can take the few data points, -40, -20, okay, like that, some 5 or 10 data points. But what if I really want to see a good curve over all the temperature, let us say in the resolution of 2 degrees centigrade? Then I have to make use of this parametric sweep. Take another case. Let us take a voltage regulator. Think of voltage regulator. Its output current varies. Let us say it varies from 1 milliamp to 1 ampere. Regulators do provide this type of currents, but how to simulate it? Can I simulate at 1 ampere, which is 1000 milliamps, then 500 milliamps, 200, or I can make a one straight sweep of the output resistor, varying from, let us say, some few ohms to few kilo ohms, which is the representation of 1000 milliamps to some low milliamps. So in this type of situation, parametric sweep can help me a lot.
So ABS Ghaziabad, now you can go ahead with your query.
My question is, my different simulators show different power dissipation to same circuit.
If I took it clearly, you are talking of power dissipation template, is it? No. Yeah, okay. Power dissipation template capability is already there in the HSpice. You can straight write .power command and find out the power consumption of your circuit. But I will say it is not very dependable thing, in the sense you can always find out the power of your circuit by V and I multiplication. That also you can do in the HSpice. You no need to do it on calculator. So just write dot measure command and use this V and I product and find out all types of power: average power, peak power, RMS power, whatever you want to know.
My question is, why is it different for different simulators?
No, see, yeah, in the simulators, there is not a commonality. One thing, uh, most of the simulators, yes, do use the same type of formats for most of the commands, but you cannot say industry is not on the open house platform where everything is having the same type of commands. Even in the Spectre and HSpice, writing a command is different. Even the case sensitivity is different in the simulators. One simulator, for example, HSpice is case insensitive, but Spectre is case sensitive. So this is again the policy of those EDA vendors to distinguish their products or whatever.
So I think.
Hello, sir. One more question from the policy. Hello.
ओपन सोर्स पे कोई मेरे करनी है ना
PSpice they can have.
The last college from JSS College Noida.
I think PSpice, some version of PSpice is there, but open source softwares are very limited in VLSI. Yes, any other query?
Yes, sir. Good afternoon, sir.
Good afternoon.
I am from Madanman Malviya University of Technology, Gorakhpur. My
Yeah,
question
please.
is, sir, which software will be best to use tunnel diode with microwave devices? Suppose we have to integrate a microwave strip filter with tunnel diode. Which software will be best?
No, I'm okay. See, as far as HSpice goes, I can tell you in this way that HSpice is capable of simulation up to 100 gigahertz.
Yes, sir.
But the tunnel diode also it is capable of modeling. This is also there, but and it is also used for the RF circuits. But regarding the microwave circuits, I don't think that HSpice is that ideal platform. You may have to go for some company called Coventer, or some Agilent companies. Agilent is the house which gives this high frequency phenomena really into account. So
Means,
maybe yeah.
means we can use ADS for this.
Yes, you can use ADS will be a better option as compared to HSpice. But again, if you properly simulate with the transmission line effects and all impedances, reflections as parameter domains, now the modern HSpice is highly capable of doing the RF work. And
Sir,
yeah, HSpice RF is the answer or ADS is the answer.
sir, but most of the time while using tunnel diode, it was not easier.
Okay, sorry, I'm not able to specifically answer your query because I'm not the man from microwave industry or the tunnel diode. I have not simulated rightly. But this background of information I can give that ADS and HSpice, sorry, RF Spectre RF can do it for you.
Thank you very much, sir.
Yeah.
So they want to ask or okay, GSS Noida, you have any query? Any other center? If any query is there from any other center?
Good evening, sir.
Good evening.
From Engineering College once again. If I am right, and what's the scope of that power statement should not be used and rather we should go over VLSI? I would like to know the reason for this thing.
Yes,
My
clear. Maybe.
power statement is what that should be.
Oh, okay. Power statement. Achha. Yeah. No. You can use the dot power statement. It's not that because it's there in the simulator anyhow, but you have to use it in this way that what type of power actually you want to measure, RMS power, DC power or the peak power, and just see that appropriate statement is being put into the simulator. If not then there is other way around. Normally what we do is like this. See, voltage is not fluctuating that much, voltage is constant. The current consumption of the circuit, if it is changing over the time, transient phenomena, then let us say I find out the average current from 1 microsecond to 10 microseconds, or the peak current from 1 microsecond to 10 microseconds, and then multiply it with the voltage. I can have the power of the circuit. Or else you can use dot power RMS, dot power DC, but just see use the right statement of the power command.
So any more query? So I think there is no more query from any nodal center. So it is time to thank our speaker from SCL Mohali, Engineer Deep Sehgal. We are really thankful to you for accepting our invitation and giving us exposure of this synopsis tool and simulators, their advantages, their drawbacks, and what are the main things that we have to consider why we have to simulate our circuit. Though all those basically inputs are really very useful for all of us, and I hope everyone enjoyed it. And now whenever you are going to simulate your circuit, you will take care of the parameters. You will try to change the parameters as per your specifications. You will not work on those default parameters only for simulation. So that is the main you can say concern. So you should be very aware of that. So now with this, we once again thanks Engineer Deep Sehgal, and we will start our tomorrow session again at 9:30. Thank you.
Thanks a lot.